The birth of the universe is the greatest story ever told, a journey that began from nothing and became everything. The stars, the galaxies, the planets, and even life itself, all of it emerged from a single moment in time. A moment so small and so powerful that it shaped the entire cosmos. To understand how the universe began, we must travel back in time, to a place before time, before space, before matter itself existed. Scientists believe that the universe was born 13.8 billion years ago, in an event known as the Big Bang. But the name Big Bang can be misleading. It was not an explosion in space, because space itself did not exist yet. Instead, it was the sudden appearance of all energy, matter, and space, expanding from a single point, smaller than an atom. This point was known as a singularity, a place of infinite density and temperature. No one knows exactly why or how it appeared, but in an instant it began to expand. Within a fraction of a second, the universe grew from a size smaller than a proton to something billions of times larger. This rapid expansion is called cosmic inflation, and it set the stage for everything that followed. As the universe expanded, it also began to cool. At first, it was too hot for anything to exist. No atoms, no light, just pure energy. But as temperatures dropped, energy began to transform into the fundamental building blocks of matter, quarks and electrons. Quarks are tiny particles that make up protons and neutrons, while electrons are the negatively charged particles that orbit atoms. But at this early stage, quarks were still too chaotic to form anything stable. The universe was like a cosmic soup, a hot and dense plasma where particles were colliding at incredible speeds, about 1/1,000,000th of a second. After the Big Bang, the universe cooled just enough for quarks to combine and form protons and neutrons. These are the particles that make up the cores of atoms, but it would take hundreds of thousands of years before these particles could come together to form actual atoms. Around 380,000 years. After the Big Bang, something incredible happened. As the universe continued to cool, protons and neutrons finally captured electrons, forming the first atoms. This process, called recombination, allowed light to travel freely for the first time. Before this, the universe was opaque, a thick fog of energy and particles. But once atoms formed, the universe became transparent, and the first light spread out into space. This light is still visible today as the cosmic microwave background radiation, a faint glow that fills the universe, acting like a snapshot of its early days. For the next few 100 million years, the universe remained dark. There were no stars, no galaxies, just vast clouds of hydrogen and helium gas drifting through space. This era is known as the Cosmic Dark Ages, a time before the first stars were born. Then, about 200 to 400 million years after the Big Bang, gravity began to take over. Tiny variations in the density of the universe caused gas clouds to collapse, forming the first stars. These stars were massive, much larger than our sun, and they burned incredibly hot, producing intense ultraviolet radiation. Their light ended the cosmic dark ages and began a period known as cosmic reionization. These early stars were different from the ones we see today. They contained only hydrogen and helium because heavier elements had not been formed yet. But inside their cores, nuclear fusion began to create new elements: carbon, oxygen, iron, and many others. These elements would later become the building blocks of planets, moons, and even life itself. But these first stars burned out quickly. Within just a few million years, many of them exploded in supernovae, releasing their elements into space. The powerful explosions also triggered the formation of new stars, leading to the birth of the first galaxies. About 1 billion years after the Big Bang, the universe was filled with galaxies, each containing billions of stars. Some of these galaxies merged, forming even larger structures. Over time, gravity continued to shape the universe, pulling galaxies into clusters and superclusters. Our own Milky Way galaxy began forming around 12 billion years ago, growing from smaller galaxies merging together. At its center, a massive black hole formed, influencing the movement of stars and gas. About 4.6 billion years ago, inside one of the spiral arms of the Milky Way, a cloud of gas and dust collapsed under its own gravity, forming a new star, a sun. Around it, leftover material came together to form planets, moons, and asteroids. This was the birth of our solar system, a tiny part of the universe, but the place we call home. The universe has continued to evolve ever since. Galaxies move, stars are born and die, and the cosmos expands at an ever-increasing rate. In fact, scientists have discovered that the expansion of the universe is accelerating, driven by a mysterious force called dark energy. What will happen next? In the far future, galaxies will drift farther apart, and new stars will form less frequently. In 100 billion years, distant galaxies will be so far away that they will no longer be visible from our galaxy. The universe will become a much darker place. In trillions of years, the last stars will burn out, and black holes will slowly consume what remains. Eventually, even black holes will evaporate, leaving behind a cold and empty universe. This is one possible fate of the universe, known as heat death, where all energy is spread so thin that nothing new can ever form. But for now, we are still in the golden age of the universe, a time filled with light, stars, and endless possibilities. From a tiny point of energy to a vast cosmic landscape, the universe has come a long way. And yet, its full story is still being written, waiting to be explored. Imagine for a moment the vast expanse beyond our planet, where the familiar blue of Earth gives way to an ocean of darkness studded with points of light. These luminous bodies are stars' massive spheres of plasma held together by gravity and powered by nuclear fusion. They serve as cosmic laboratories, each one operating under physical principles that govern the behavior of matter and energy across billions of years. While their light reaches us after traversing unfathomable distances, it carries with it detailed information about the conditions of their formation, composition, and evolution. As you continue to relax, consider the scientific significance of the vacuum of space. In stark contrast to the dense, turbulent environment of our atmosphere, space is characterized by its near-perfect vacuum region where matter is exceedingly sparse, and interactions occur under conditions rarely replicated on Earth. This environment allows for the propagation of electromagnetic radiation in its purest form, providing us with data from telescopes that observe in wavelengths, ranging from radio waves to gamma rays. These observations have profoundly expanded our understanding of everything from the life cycles of stars to the expansion of the universe itself. The universe is structured on a scale that defies everyday experience. Our own Milky Way galaxy, a barred spiral system containing hundreds of billions of stars, is but one component of a vast cosmic network. Galaxies like our own are organized into clusters and superclusters, interconnected by filaments of dark matter that create what cosmologists refer to as the cosmic web. This large-scale structure is not random. It is the result of gravitational interactions over billions of years, influenced by the initial conditions set in the aftermath of the Big Bang. As we reflect on these immense structures, we recognize that the same fundamental forces that shape the motion of planets and stars are at work on the grandest scales imaginable. Consider also the phenomena that occur in the depths of space, such as nebulae, enormous clouds of gas and dust where new stars are born. These regions of ionized hydrogen, helium, and trace elements are not only visually striking, but are also critical to the process of stellar evolution. The radiation from young stars interacts with the surrounding material, triggering complex chemical reactions and eventually, the formation of new stellar systems. In a sense, nebulae are the crucibles in which the elements essential to life are forged, their processes governed by the same physics that underpins everything from atomic interactions to the thermodynamic principles of energy transfer. As you listen, allow your mind to appreciate the delicate balance maintained in these cosmic processes. The intricate interplay between gravitational collapse and thermal pressure in star-forming regions illustrates the fundamental equilibrium that governs much of the universe's behavior. In the calm of this exploration, we are reminded that even phenomena on scales of light-years can be described by equations and principles that resonate with simplicity and elegancia, testament to the universality of physical laws. Moving further along our journey, we now direct our attention to the study of planetary systems. Our own solar system, with its 8 primary planets, countless moons, and smaller bodies such as asteroids and comets, serves as a microcosm of cosmic evolution. The planets orbit our Sun in a predictable and orderly fashion, their trajectories determined by the gravitational pull of our star. This regular motion is described by Kepler's laws of planetary motion and Newton's law of universal gravitation, both of which remain central to modern astrophysics. By studying the solar system in detail, scientists have gleaned insights into the processes that govern planetary formation, the conditions necessary for life, and the dynamic evolution of celestial bodies over time. Beyond our solar system lie exoplanets' worlds, orbiting distant stars that present a diverse array of environments. Some of these exoplanets reside in the so-called habitable zone, where conditions might allow for liquid water and potentially life. The discovery and study of these distant worlds have transformed our understanding of planetary diversity and have provided a broader context for the existence of our own planet. Each exoplanet is a data point in a larger narrative about the formation of solar systems and the potential for life elsewhere in the universe. In parallel with our understanding of stars and planets is the study of the more enigmatic phenomena that punctuate our cosmic landscape. Black holes, for instance, are regions of space-time where gravity is so intense that not even light can escape. Formed from the remnants of massive stars or existing as supermassive entities at the centers of galaxies, black holes challenge our understanding of physics and push the boundaries of general relativity. The study of these objects has not only deepened our comprehension of gravitational phenomena, but has also provided insights into the behavior of matter under extreme conditions, a subject of ongoing research and debate among physicists. As you relax further into this exploration, consider how the interplay of science and observation brings clarity to our understanding of such complex topics. With advanced instruments like the Hubble Space Telescope, the Chandra X-ray Observatory, and the more recent James Webb Space Telescope, astronomers have been able to observe the universe with unprecedented precision. These tools allow us to peer into regions that were once hidden behind cosmic veils, revealing detailed images of star-forming regions, the structure of galaxies, and even the subtle fluctuations in the cosmic microwave background, the afterglow of the Big Bang. The cosmic microwave background itself is a profound subject of scientific inquiry. This relic radiation permeates the universe, offering a snapshot of the cosmos approximately 380,000 years after its inception. By analyzing the slight variations in this radiation, scientists can infer the distribution of matter and energy in the early universe, providing critical evidence for the theory of cosmic inflation and the subsequent evolution of large-scale structures. The study of this radiation is a prime example of how careful observation, guided by theoretical models, can yield insights into events that occurred billions of years ago. In reflecting on these scientific principles, it is worth considering the inherent beauty found in the rigor and precision of the natural laws that govern the cosmos. The same equations that describe the motion of distant galaxies also explain the trajectory of a falling apple. This unity of natura harmony between the microcosm and the macrocosm provides not only a framework for understanding our universe, but also a source of deep intellectual and aesthetic satisfaction. As you listen, allow the steady, rational progression of scientific thought to instill in you a sense of calm and wonder. This journey is a reminder that the cosmos is not a chaotic, unapproachable expanse, but a domain of order and predictability, governed by universal principles. Each discovery, whether it pertains to the life cycle of a star, the mechanics of planetary orbits, or the subtle signals from the early universe, reinforces our understanding of the interconnectedness of all things. In the pursuit of knowledge, we find that the universe, in all its complexity, follows a set of patterns that can be discerned, measured, and appreciated even in moments of quiet contemplation. As you continue to listen and let your mind settle into this state of focused relaxation, consider the profound impact that scientific inquiry has had on humanity. Our quest to understand the cosmos has not only advanced technology and enriched our culture, but has also provided a framework for contemplating our place within the vast expanse of space and time. The same methods that guide astronomical research, observation, hypothesis, experimentation, and analysis are a testament to human curiosity and the desire to uncover the truths of nature. Now, as we conclude this introductory segment, take a moment to appreciate the calm order that underlies the universe. Each pulsation of distant stars, each subtle ripple in the fabric of space-time, and each carefully observed datum contributes to a grand tapestry of cosmic understanding. In this moment, let the steady rhythm of scientific discovery encourage you to relax further, knowing that the journey ahead will reveal more about the natural laws that shape our reality. Allow the depth and clarity of scientific insight to guide you into a state of peaceful reflection as we continue our voyage through the vast and meticulously ordered universe. Space is often described as a vast, silent, expansive notion that at first may seem counterintuitive, given the constant activity and energy radiating from stars, galaxies, and cosmic events. However, this silence arises from the fundamental nature of sound itself. Sound is a mechanical wave that requires a medium such as air, water, or solid matter to propagate. In the absence of such a medium, as is the case in the near vacuum of space, sound waves cannot travel. The molecules present in a medium vibrate in response to an oscillation, transferring energy from one molecule to the next in a process that we perceive as sound. Without these molecules to collide and transmit vibrational energy, there is no mechanism for sound to be carried across the void. At the heart of this concept is the idea that sound is inherently tied to matter. On Earth, our atmosphere, composed primarily of nitrogen and oxygen, serves as an excellent medium for the transmission of sound waves. The density of this medium allows for efficient molecular interactions, enabling sound to travel distances ranging from a few meters to several kilometers, depending on the frequency and energy of the sound wave. In contrast, space is an environment where particles are so sparsely distributed that they are unable to sustain the continuous chain of molecular collisions required for the propagation of sound. Even in regions where there is some matter such as interstellar clouds or the sparse plasma found in the solar wind, the density is many orders of magnitude lower than that of an atmosphere on Earth. Consequently, any mechanical wave initiated in these regions would rapidly dissipate, rendering the environment effectively silent. This phenomenon also highlights an important distinction between different types of waves in physics. Unlike sound, electromagnetic waves, including visible light, radio waves, and X-rays, do not require a medium to travel. They are oscillations of electric and magnetic fields that can propagate through a vacuum at the speed of light. This fundamental difference allows us to observe distant astronomical objects using telescopes that detect various wavelengths of electromagnetic radiation, even though the objects themselves might be surrounded by the near-total silence of space. The ability of electromagnetic waves to traverse the vacuum of space has been critical to our understanding of the cosmos, enabling us to receive light and information from stars and galaxies that are billions of light-years away. Understanding why space is silent also deepens our appreciation for the principles of energy transfer and wave mechanics. In a typical terrestrial environment, sound waves are classified as longitudinal waves, meaning that the displacement of the medium occurs in the same direction as the wave travels. This is distinct from transverse waves, such as those observed in electromagnetic phenomena, where the oscillation occurs perpendicular to the direction of propagation. The efficiency of energy transfer in these wave types is highly dependent on the characteristics of the medium through which they travel. In a vacuum, the absence of a medium means that the energy cannot be effectively transferred from one location to another via mechanical means, and thus the concept of sound becomes irrelevant. Moreover, the silent nature of space provides a fascinating context for discussing the interplay between pressure, density, and wave propagation. In environments where the medium is dense and the pressure is high, such as in the lower atmosphere or underwater, sound travels quickly and with little loss of energy over short distances. As the density and pressure of the medium decrease, so too does the efficiency of sound transmission. This is why, even on Earth, in high-altitude regions where the air is thin, sound does not travel as effectively as it does at sea level. Extrapolating this concept to the extreme conditions of space, where the density of particles is nearly negligible, reinforces the notion that mechanical waves like sound simply cannot find a substrate through which to move. In addition to these fundamental physical principles, the quietness of space also has practical implications for space exploration and technology. For example, communication between spacecraft and ground stations on Earth relies not on sound, but on electromagnetic signals transmitted through radio waves. These signals are not subject to the limitations of sound propagation and can cover the vast distances of space with minimal loss of fidelity. The engineering challenges of designing these communication systems underscore the importance of understanding the medium or lack thereof through which different types of waves travel. In summary, the silence of space is a direct consequence of the fact that sound, as a mechanical wave, depends entirely on the presence of a medium to facilitate the movement of energy through molecular vibrations. Without the dense concentrations of molecules found in atmospheres or other mediums, the vacuum of space cannot support the propagation of sound waves. This understanding not only demystifies the quiet nature of space, but also emphasizes the elegant interplay of physical laws that govern wave phenomena. While space may be silent to our ears, it is far from empty-filled instead, with electromagnetic signals that carry the luminous evidence of cosmic events across unimaginable distances. This duality between silence and signal forms one of the many intriguing aspects of our universe, blending the stark precision of scientific laws with the profound beauty of the cosmos. Stars with extraordinarily long lifespans, sometimes estimated to endure for trillions of years, are among the most fascinating objects in astrophysics. These stars, predominantly red dwarfs, represent a class of low-mass stars that burn their nuclear fuel at an incredibly slow rate. This slow pace of nuclear fusion allows them to consume hydrogen at such a gradual rate that their lifetimes extend well beyond the current age of the universe. The longevity of red dwarf stars is primarily due to two interrelated factors: their efficient use of fuel and the physical laws that govern stellar evolution. In stars like our Sun, hydrogen fusion occurs at a relatively rapid pace in the core, leading to a gradual buildup of helium and a finite fuel supply that determines the star's lifetime, roughly 10 billion years. In contrast, red dwarfs operate under conditions where the temperature and pressure are significantly lower, resulting in a fusion rate that is orders of magnitude slower. This efficiency means that red dwarfs can potentially continue fusing hydrogen for up to several trillion years, a time frame that far exceeds the approximately 13.8 billion years since the Big Bang. Another critical aspect of red dwarf longevity is their fully convective interiors. Unlike more massive stars, which have a layered structure with distinct radiative and convective zones, many red dwarfs are completely convective. This property ensures that hydrogen fuel is continuously mixed throughout the entire star, rather than being confined to the core. As a result, nearly all of the star's hydrogen can be used for fusion over its lifetime, maximizing fuel consumption and further prolonging its existence. From a theoretical standpoint, the slow-burning nature of red dwarfs offers an intriguing glimpse into the far future of the universe. While more massive stars will evolve, explode as supernovae, or collapse into neutron stars and black holes, red dwarfs are expected to persist as stable, dim beacons for periods that extend into the cosmic future. In models of stellar evolution, once all the available hydrogen in a red dwarf is exhausted, these stars will eventually transition into a cooling phase as white dwarfs. However, because their initial fusion processes are so prolonged, the transformation to a white dwarf is delayed far into the future, ensuring that red dwarfs remain the dominant type of star long after many other stellar populations have faded. Observationally, red dwarfs are also abundant in our own galaxy. They make up roughly 70 to 80% of all stars in the Milky Way, making them the most common type of star in our cosmic neighborhood. Despite their abundance, their low luminosity means they are often overlooked when surveying the sky. Modern astronomical techniques, particularly those involving infrared observations, have significantly improved our ability to detect and study these faint objects, allowing scientists to refine estimates of their masses, compositions, and lifespans. The study of these long-lived stars not only enriches our understanding of stellar physics, but also has implications for the search for extraterrestrial life. Because red dwarfs live for such immense periods, any planetary systems orbiting these stars have an extended window of stability during which life could potentially develop. However, the habitability of planets around red dwarfs is a complex topic. Factors such as stellar flare activity and tidal locking pose challenges, yet the sheer longevity of these stars provides a tantalizing possibility. Life, if it were to emerge under the right conditions, could have vast amounts of time to evolve and adapt. In summary, the longest living stars in the universe, primarily red dwarfs, owe their extended lifetimes to their low mass, slow fusion rates, and fully convective interiors. Their ability to burn hydrogen at such a measured pace means that they can exist for trillions of years, far longer than stars like our Sun. As we continue to explore the cosmos, red dwarfs not only serve as laboratories for understanding the physics of stellar evolution, but also as potential hosts for planets where life might persist in the far future. Their enduring nature offers a profound perspective on the evolution of the universe and the ongoing processes that shape it over incomprehensible timescales. Planets orbit due to the fundamental force of gravity, which governs the motion of objects with mass throughout the universe. At the heart of orbital motion is Newton's law of universal gravitation, which states that every two bodies exert an attractive force on each other proportional to the product of their masses and inversely proportional to the square of the distance between them. In the context of a planetary system, a star's immense mass creates a gravitational field that attracts orbiting planets, compelling them to follow curved trajectories rather than moving in straight lines. This gravitational pull provides the necessary centripetal force that continuously alters the direction of a planet's velocity, keeping it in orbit. According to Newtonian mechanics, if a planet were moving in a straight line without the influence of gravity, it would continue indefinitely in that direction due to inertia. However, because the star's gravity constantly pulls the planet toward it, the planet's path is deflected into an elliptical orbiter phenomenon, elegantly described by Kepler's laws of planetary motion. Kepler's first law, for instance, tells us that the orbit of a planet is an ellipse with the star at one of its foci, rather than a perfect circle, which accounts for the variations in a planet's distance from its star over time. In these elliptical orbits, a planet's speed is not constant. Kepler's second law, often referred to as the law of equal areas, states that a line connecting a planet to its star sweeps out equal areas during equal intervals of time. This means that a planet moves faster when it is closer to the star at its perihelion, and slower when it is farther away at its aphelion. This variation in orbital speed is a natural consequence of the conservation of angular momentum, a fundamental principle in physics that ensures the product of the orbital speed and the distance from the star remains constant, barring external forces. While classical mechanics provides an excellent description of planetary orbits, the theory of general relativity offers a more comprehensive framework, particularly in extreme gravitational field. Einstein's theory posits that massive objects, like stars, cause a curvature in spacetime. Planets follow the geodesics essentially, the straightest possible paths in this curved spacetime, which we interpret as elliptical orbits. In many everyday cases within our solar system, the predictions made by Newtonian physics and general relativity closely agree. However, the relativistic corrections become significant in systems with very massive bodies, or when objects are in close proximity to these masses. Additionally, the stability of planetary orbits is influenced by the interplay of gravitational forces among all the bodies in a system. In multi-planet systems, gravitational interactions can lead to small deviations or perturbations in the orbit of each planet. Over long periods, these perturbations can result in variations in orbital eccentricity and inclination, and in some cases, can even lead to resonance situations where the orbital periods of two or more planets are in simple numerical ratios. These resonances can stabilize or destabilize orbits depending on the configuration and mass distribution of the planetary system. The process of orbital formation itself is rooted in the dynamics of the protoplanetary rotating disk of gas and dust that surrounds a young star. Through a combination of accretion and gravitational interactions, particles within the disk gradually coalesce to form planetesimals, which then merge to form fully developed planets. As these nascent bodies interact gravitationally, they settle into orbits that reflect the conservation of momentum and energy present in the original disk. Over time, these orbits become more defined and stable, although they may continue to evolve due to ongoing gravitational interactions and external influences, such as nearby stars or molecular clouds. In summary, the orbit of a planet is the result of a delicate balance between inertia tendency of a planet to move in a straight line and the gravitational pull of a star, which continuously alters that motion into a curved path. This interplay, described by both Newtonian mechanics and refined by Einstein's general relativity, results in the elliptical trajectories that planets follow. Understanding these dynamics not only deepens our knowledge of celestial mechanics, but also provides critical insights into the formation and long-term stability of planetary systems throughout the universe. The closest star to our solar system is Proxima Centauri, a faint red dwarf located approximately 4.24 light-years away. It is part of the Alpha Centauri star system, which also includes two star-like companions, Alpha Centauri A and Alpha Centauri B. These two orbit each other in a close binary configuration, while Proxima Centauri moves in a much wider, elongated orbit around them. This makes Proxima Centauri a gravitationally bound but distant companion to the system, and as the closest known star, it has long been a subject of great interest to astronomers. Proxima Centauri is classified as an M-type red dwarf, the most common type of star in the Milky Way galaxy. These stars are much smaller, cooler, and dimmer than the average star, burning their hydrogen fuel at an extremely slow rate. With only about 12% of the mass of a typical star and a surface temperature of around 3,000 degrees Celsius, compared to the 5,500 degrees Celsius of a star like Alpha Centauri A, Proxima Centauri emits only a fraction of the light of its larger counterparts. This is why, despite being the nearest star, it is invisible to the naked eye from Earth. One of the most fascinating aspects of Proxima Centauri is its extreme longevity. While larger stars have lifetimes of about 10 billion years, red dwarfs such as Proxima Centauri can persist for hundreds of billions or even trillions of years. This is because they consume their hydrogen fuel so slowly that they are expected to remain active long after more massive stars have exhausted their fuel and faded into white dwarfs. However, Proxima Centauri is also classified as a flare star, meaning it experiences sudden and powerful eruptions of energy. These stellar flares can release massive amounts of radiation, which has significant implications for any planets that may orbit the star. Proxima Centauri is known to host at least 2 exoplanets, with a possible third candidate awaiting confirmation. The most famous of these is Proxima Centauri b, a rocky, Earth-sized planet that orbits the star at a distance of about 7.3 million kilometers, far closer than Mercury is to the average star it orbits. However, because Proxima Centauri is so dim, this close orbit places the planet in the star's habitable zone, the region where temperatures might allow liquid water to exist on the surface. Proxima b has a mass about 1.17 times that of Earth, making it a terrestrial planet that could, in theory, have Earth-like conditions. Despite its position in the habitable zone, Proxima b's habitability is uncertain. One major challenge is the extreme radiation environment created by Proxima Centauri's flares. The star frequently emits powerful bursts of X-rays and ultraviolet radiation, which could strip away the planet's atmosphere over time. If Proxima b lacks a strong magnetic field like Earth's, it may have already lost much of its protective atmosphere, making it unlikely to support life as we know it. However, if it has managed to retain an atmosphere or has a subsurface ocean, it could still be a candidate for habitability. Another factor that complicates Proxima b's potential for life is its likely tidal locking. Because it orbits so close to its star, gravitational interactions would have slowed its rotation, possibly causing one side of the planet to face the star permanently, while the other remains in perpetual darkness. This would create a stark contrast in temperature between the two hemispheres, with one side potentially too hot and the other too cold for life. However, if there is an atmosphere capable of distributing heat, or if an ocean exists, conditions might be more stable in a twilight zone between the two extremes. In addition to Proxima b, astronomers have detected another exoplanet in the system, Proxima Centauri c. This planet is much farther from the star, orbiting at a distance of about 1.5, roughly the same distance as Mars from an average star. Unlike Proxima b, which is a rocky world, Proxima c is thought to be a super-Earth or mini-Neptune, possibly with a thick atmosphere or a layer of ice. Due to its distance from the star, it is far outside the habitable zone and likely too cold to support liquid water on its surface. There is also evidence suggesting the presence of a third planet, Proxima d, which would be even smaller than Proxima b. If confirmed, it would be one of the lightest exoplanets ever discovered, with only about a quarter of Earth's mass. It orbits extremely close to the star, completing a full orbit in just 5 days. Because of its proximity, it is unlikely to be habitable, as temperatures would be far too high. Proxima Centauri and its planets continue to be a major focus of scientific research, particularly in the search for extraterrestrial life. Given its proximity to Earth, it is one of the best places to study exoplanets up close, and it has been considered a prime target for future interstellar missions. Concepts such as the Breakthrough Starshot initiative propose sending tiny, high-speed spacecraft propelled by laser-driven sails to Proxima Centauri, potentially allowing us to capture images and data from its planetary system within a few decades. While much remains unknown about Proxima Centauri and its planets, ongoing advancements in telescope technology are helping scientists learn more. Instruments such as the James Webb Space Telescope and next-generation ground-based observatories are expected to provide more detailed insights into the atmospheres, compositions, and conditions of these distant worlds. As we continue to explore, Proxima Centauri may hold some of the first clues about what lies beyond our own planetary system, offering a glimpse into the vast and diverse array of planetary systems that populate our galaxy. The universe is an immense expanse, filled with countless galaxies, each containing billions or even trillions of stars. Within our own galaxy, the Milky Way, stars are scattered like shimmering islands in an endless cosmic ocean. From massive blue giants burning at extreme temperatures to faint red dwarfs glowing softly in the darkness, each star is a beacon of energy, illuminating the void of space. Some stars blaze with intense luminosity, outshining entire regions of their galaxies, while others remain barely visible, their light taking thousands or even millions of years to reach us. Stars are born within vast clouds of gas and dust, known as nebulae. These regions, often called stellar nurseries, are filled with hydrogen and other elements that slowly collapse under the pull of gravity. As the gas condenses, it heats up, and deep within these clouds, the first sparks of fusion ignite. This process marks the birth of a new star, a celestial furnace that will burn for millions or even trillions of years, depending on its mass. The larger the star, the more quickly it burns through its fuel, while smaller ones glow faintly but endure for unimaginable timescales. As stars form, they often gather into clusters, bound together by their mutual gravitational pull. Some of these clusters remain tightly packed, while others slowly drift apart over time. Throughout the Milky Way, stars swirl in a grand spiral, moving along with the immense rotation of the galaxy. While individual stars may seem stationary from our perspective, they are actually hurtling through space at incredible speeds, taking hundreds of millions of years to complete a single orbit around the galactic center. The light from distant stars has traveled across unfathomable distances to reach our eyes. Some of the starlight we see today began its journey before human civilization even existed. Looking up at the night sky is like peering back in time, witnessing ancient stars that may have long since burned out, their light only now arriving after a voyage lasting thousands or even millions of years. Throughout the universe, stars form the very foundation of planetary systems. Around them, planets take shape from swirling disks of dust and gas, gradually coalescing into new worlds. Some of these planets may remain barren and lifeless, while others could develop the conditions necessary for life. Among the countless stars scattered across the cosmos, the possibility of habitable planets orbiting distant stars raises the question of whether life exists beyond our own world. Stars do not shine forever. Eventually, they exhaust their nuclear fuel, leading to extraordinary transformations. The most massive stars explode in violent supernovae, scattering heavy elements across space and seeding new generations of stars and planets. Others swell into immense red giants before shedding their outer layers, leaving behind a dense, glowing remnant. The faintest stars fade slowly, their light gradually dimming as they drift into the depths of time. The night sky, filled with billions of stars, is a reminder of the vastness of the cosmos. Every point of light represents an immense, burning sphere of plasma, many with their own planets, moons, and possibly even life. The universe is a vast, ever-changing expanse, with galaxies teeming with stars, each one a beacon of cosmic history. Whether viewed through a telescope or simply gazed upon from Earth, the stars tell the story of the universe itself, story of creation, transformation, and infinite wonder. Scattered throughout the vast expanse of the Milky Way, beyond the familiar planets of our own solar system, lie countless exoplanets worlds that orbit stars other than our own. For centuries, the idea of other planets beyond our solar system was purely speculative, but with the advent of powerful telescopes and advanced detection techniques, astronomers have confirmed the existence of thousands of exoplanets, with estimates suggesting that there may be billions more hidden within our galaxy. These distant worlds vary in size, composition, and conditions, ranging from scorching gas giants many times the size of Jupiter, to rocky, Earth-like planets that may harbor liquid water and possibly even life. Exoplanets are found in nearly every corner of the Milky Way, orbiting stars of all types, from blazing blue giants to dim red dwarfs. Some cling tightly to their parent stars, completing orbits in a matter of days, while others drift in vast, elongated paths that take them hundreds of years to circle their host star. Some exoplanets, known as rogue planets, have no star at all, wandering the galaxy alone in the cold darkness of interstellar space. The diversity of these alien worlds has reshaped our understanding of planetary formation, revealing that the cosmos is filled with planets in an astonishing variety of forms, many of which defy our expectations. Among the most intriguing discoveries are the rocky exoplanets that fall within the habitable zones of their stars, the regions where temperatures might allow liquid water to exist. One of the most famous is Proxima Centauri b, located just 4.24 light-years away, orbiting the closest star to our solar system. This world, similar in size to Earth, sits within its star's habitable zone, raising the possibility that it could support conditions favorable for life. However, its parent star is a red dwarf, known for its intense stellar flares, which may have stripped away Proxima b's atmosphere, making it an inhospitable place. Beyond our nearest neighbor, the Milky Way is teeming with other fascinating exoplanets. The TRAPPIST-1 system, located about 40 light-years away, contains 7 Earth-sized planets orbiting a faint red dwarf star. 3 of these worlds reside in the star's habitable zone, making this one of the most promising places to search for signs of extraterrestrial life. The planets in this system are so close to one another that an observer standing on one of them might see neighboring planets appearing larger in the sky than our own moon. The compact nature of this system challenges traditional models of planetary formation, showing that planets can form in tightly packed arrangements around even the smallest of stars. Some exoplanets are far more extreme than anything found in our solar system. Gas giants, known as hot Jupiters, orbit their stars at blistering speeds, completing revolutions in just a few days. These planets, such as 51 Pegasi b, were among the first exoplanets ever discovered, and their existence surprised astronomers because they challenged previous theories of planetary formation. Instead of forming far from their stars like Jupiter and Saturn, these massive planets likely formed farther out and later migrated inward due to gravitational interactions. Other exoplanets exist in exotic environments where conditions are beyond anything imaginable on Earth. Take HD 189,733b, for example, a gas giant where violent glass shard-filled winds blow at speeds of up to 8,700 kilometers per hour, faster than the speed of sound. Another, known as WASP-12b, orbits so close to its star that it is being gradually ripped apart by intense gravitational forces, slowly dissolving into space. Then there is Kepler-10b, an ultra-dense planet composed almost entirely of iron, with a surface hot enough to melt metal. One of the most exciting aspects of exoplanet research is the search for biosignature chemical traces in planetary atmospheres that might indicate the presence of life. Future telescopes, such as the James Webb Space Telescope and the upcoming Extremely Large Telescope, will allow scientists to analyze the atmospheres of distant exoplanets in unprecedented detail. By studying the light that filters through these atmospheres, researchers can detect elements like oxygen, methane, and carbon dioxide gases that, on Earth, are strongly linked to biological activity. If such signatures are found on a distant world, it could be the first hint that life exists beyond our planet. Yet, even as scientists push the boundaries of discovery, they know that what has been found so far is only the beginning. The Milky Way alone contains an estimated 100 to 400 billion stars, and if most of them host planets as observations suggest there could be trillions of exoplanets waiting to be discovered. Some of these planets may be eerily similar to Earth, while others may be unlike anything we can yet imagine. The sheer variety and abundance of exoplanets tell us one undeniable truth. Our solar system is not unique, and the Milky Way is filled with planetary systems, each with its own story to tell. As technology advances, the dream of directly imaging these distant worlds is becoming a reality. Future space missions aim to capture detailed pictures of exoplanets, revealing their colors, weather patterns, and even possible land masses or oceans. One day we may see the surface of a distant, Earth-like exoplanet with our own ISA moment that could redefine humanity's place in the universe. For now, each new discovery adds another piece to the cosmic puzzle, showing us that the Milky Way is not just a galaxy of stars, but a galaxy of worlds, each with the potential to hold wonders beyond our imagination. The Milky Way, our home galaxy, is a vast and majestic spiral, rotating slowly yet relentlessly through the cosmos. Though it appears still from our vantage point on Earth, it is in constant motion. Its billions of stars, gas clouds, and dark matter bound together by gravity, moving in a slow and graceful dance that has persisted for billions of years. Spanning about 100,000 light-years across, the Milky Way completes a single rotation, roughly once every 225 to 250 million years timescale. So immense that even the rise and fall of entire species on Earth is but a fleeting moment in its cosmic journey. At the heart of the Milky Way lies a powerful force that governs much of its motion. Sagittarius A, a supermassive black hole millions of times the mass of a typical star. Surrounding this enigmatic core, stars and cosmic dust swirl in a dense, energetic region, their orbits dictated by the immense gravitational pull of this invisible giant. Moving outward, the galaxy's spiral arms extend like flowing streams of stardust, winding around the galactic center in an elegant spiraling structure. These arms, filled with newborn stars, glowing nebulae, and ancient stellar remnants, rotate at different speeds depending on their distance from the core. Unlike a solid object, the Milky Way's rotation is differential, meaning that stars closer to the center complete their orbits much faster than those on the outskirts. This creates a dynamic yet stable system, where billions of celestial bodies, from massive blue supergiants to faint red dwarfs, follow their own paths, maintaining the overall structure of the galaxy over eons. Our own solar system is located in one of these spiral arms, the Orion Arm, about 27,000 light-years from the galactic center. As it drifts through space, our planetary system orbits the Milky Way at an average speed of 828,000 kilometers per hour, an incredible velocity that is imperceptible to us due to the vast scales involved. The motion of the Milky Way is not limited to its own rotation. The entire galaxy itself is moving through space, traveling at over 2.1 million kilometers per hour as it drifts toward the Andromeda Galaxy, our massive neighboring spiral. In a distant future, billions of years from now, these two colossal galaxies will merge, forming an even larger galactic structure in a slow, gravitationally driven dance. This process, though immense, will be so gradual that the stars within each galaxy will rarely collide, instead shifting into new orbits within the newly formed galactic body. Despite its grand and elegant motion, the Milky Way is not an isolated island in space. It belongs to the local group, a small cluster of more than 50 galaxies bound together by gravity. Within this group, the Milky Way exerts its own gravitational influence, pulling on smaller satellite galaxies such as the Large and Small Magellanic Clouds, which slowly orbit our galaxy in an intricate cosmic ballet. Over time, some of these satellite galaxies may be absorbed into the Milky Way, their stars becoming part of our own celestial home. The rotation of the Milky Way is a quiet, ceaseless movement, shaping the structure of our galaxy while carrying us on an incredible journey through the universe. Though we may not feel its motion, every star, planet, and cloud of cosmic dust is drifting together, woven into the vast, ever-turning tapestry of the cosmos. As we gaze at the night sky, the countless stars above us are not fixed points but travelers in a grand cosmic rotation each, one part of a story billions of years in the making. In the vastness of the universe, hidden at the centers of galaxies, lie some of the most enigmatic and powerful objects ever discovered: supermassive black holes. These cosmic giants, millions to billions of times the mass of an average star, dominate the gravitational landscape of their galaxies, shaping the movement of stars and influencing the evolution of entire galactic structures. Despite their immense power, many of these black holes remain eerily silent, their presence detectable only through their gravitational effects, rather than the violent outbursts of energy that some of their active counterparts produce. These are the sleeping giants of the cosmos, dormant supermassive black holes, waiting in the darkness. Unlike smaller black holes formed from the collapse of massive stars, supermassive black holes exist on a completely different scale. Found at the hearts of galaxies, these behemoths grow over billions of years, consuming vast amounts of gas, dust, and even entire stars. However, not all of them are currently feeding. When a supermassive black hole runs out of material to devour, it enters a quiet, dormant state. Instead of radiating enormous amounts of energy, as seen in active galactic nuclei and quasars, these sleeping black holes lurk in the shadows, exerting an invisible yet profound influence on their surroundings. One such silent giant is the supermassive black hole at the center of our own Milky Way, Sagittarius A. With a mass roughly 4.3 million times that of an average star, it sits at the heart of our galaxy, its gravitational pull guiding the orbits of countless stars in the dense galactic core. Despite its incredible size, Sagittarius A is currently inactive, consuming only trace amounts of gas and dust. If it were actively feeding, it would shine with the brilliance of a quasar, outshining the entire galaxy. Instead, it remains in a quiet slumber, detectable primarily through the movement of stars around it. Dormant supermassive black holes are scattered throughout the universe, embedded within galaxies of all shapes and sizes. Some are remnants of once active quasars, galaxies that blazed with unimaginable brightness in the early universe, but have since quieted down as their central black holes exhausted their fuel supply. Others may awaken sporadically, reigniting for brief periods when a wandering star or a cloud of gas strays too close. In such events, known as tidal disruption events, the black hole's immense gravitational pull rips the unlucky object apart, generating bursts of radiation before the material is swallowed into oblivion. Though they may seem inactive, these sleeping giants continue to play a crucial role in shaping the galaxies they inhabit. Their gravitational fields help maintain the structure of galaxies, anchoring billions of stars in stable orbits. In some cases, their influence extends far beyond their immediate surroundings, affecting star formation rates and even determining the overall shape and rotation of their host galaxies. Scientists suspect that most large galaxies harbor a supermassive black hole at their center, yet many remain undetected due to their dormancy. However, future telescopes and observational techniques are improving our ability to locate and study these hidden colossi. By observing how stars move near the galactic center, researchers can infer the presence of a black hole even if it emits no detectable radiation. The Event Horizon Telescope, which famously captured the first ever image of a black hole's event horizon, is pushing the boundaries of what we can see, allowing us to peer into the shadows where these sleeping giants reside. The question of how these black holes formed in the first place remains one of the greatest mysteries in astrophysics. Unlike stellar mass black holes, which originate from the collapse of massive stars, supermassive black holes appear to have existed since the early universe, growing to immense sizes in relatively short cosmic timescales. Some theories suggest that they began as massive gas clouds that collapsed directly into black holes, bypassing the star formation stage entirely. Others propose that they formed from the merger of smaller black holes over millions of years. Regardless of their origins, these giants continue to shape the fate of galaxies on a scale that defies human comprehension. While many supermassive black holes lie dormant, they are not permanently asleep. Given the right circumstances, they can awaken, unleashing some of the most energetic phenomena in the universe. If a large enough amount of matter falls into their grasp, the gravitational forces generate intense friction and heat, creating disks of glowing plasma that radiate powerful jets of energy across millions of light years. Some of the most extreme examples are quasars, where feeding black holes become so luminous that they can outshine entire galaxies. For now, the sleeping giants of the cosmos remain hidden, waiting in the depths of time and space. Their silence does not mean they are inactive, rather, they are biding their time, shaping the universe in ways we are only beginning to understand. As our technology advances, we may one day witness the reawakening of one of these behemoths, a reminder that even in the darkness of space, the most powerful forces in the universe never truly disappear. They merely sleep, waiting for the next great cosmic event to stir them from their slumber. Drifting through the vast expanse of the cosmos, galaxies move like islands suspended in a boundless ocean of darkness. Each one, a colossal collection of stars, gas, dust, and dark matter, floats silently through the fabric of space, carried along by the invisible currents of gravity and the relentless expansion of the universe. Their movement is slow on human timescales, but across millions and billions of years, galaxies undergo breathtaking journey spinning, colliding, and sometimes merging in cosmic dances that shape the universe itself. Galaxies are not static objects, they are in perpetual motion, each following its own trajectory through space. This motion is driven by multiple forces, the most significant being the expansion of the universe. Since the Big Bang, space itself has been stretching, pushing galaxies apart like dots on an inflating balloon. This expansion means that, on the largest scales, galaxies are receding from one another at incredible speeds, with the most distant galaxies moving away so rapidly that their light is shifted into longer, redder wavelengths, a phenomenon known as redshift. Despite this overall expansion, gravity continues to play a dominant role in shaping the movements of galaxies on smaller scales. Within clusters and groups of galaxies, gravitational interactions keep them bound together, preventing them from simply drifting apart. The Milky Way, for example, is part of the Local Group, a collection of more than 50 galaxies, including the Andromeda Galaxy, the Triangulum Galaxy, and numerous smaller dwarf galaxies. Within this group, galaxies move in slow, intricate orbits, their mutual gravitational pulls constantly altering their trajectories. One of the most fascinating aspects of galactic motion is the way galaxies rotate. Spiral galaxies like our own exhibit a majestic spin, with their arms sweeping gracefully around a central core. This rotation is puzzling because, based on visible matter alone, the outer edges of galaxies should move much more slowly than the inner regions. However, observations reveal that stars at the outskirts of galaxies orbit just as fast as those closer to the center. This discrepancy led scientists to propose the existence of dark matter, an unseen substance that exerts gravitational influence, keeping galaxies from flying apart. Without dark matter, our current understanding of galactic motion would be incomplete. Beyond their slow rotations, galaxies also experience complex interactions with one another. While the universe is expanding, galaxies that are gravitationally bound can still move toward each other. One of the most dramatic examples of this is the impending collision between the Milky Way and the Andromeda Galaxy. Though currently separated by about 2.5 million light-years, these two massive galaxies are slowly being drawn together by their mutual gravity. In roughly 4.5 billion years, they will collide, merging into a single, enormous, elliptical galaxy. Despite the seeming violence of such an event, individual stars within these galaxies will mostly remain unaffected, as the vast distances between them mean direct collisions are rare. Instead, the interaction will trigger waves of star formation as gas clouds compress, creating new generations of stars. Galaxies also move through space in grand cosmic highways known as the cosmic web. This vast structure is composed of filaments of dark matter and gas, forming an intricate network that connects galaxies and clusters across the universe. Within these filaments, galaxies migrate over billions of years, slowly flowing toward regions of higher density. Some are drawn into massive galaxy cluster enormous gatherings of hundreds or thousands of galaxies, all bound together by gravity. Others may be ejected into the emptiness of intergalactic space, destined to drift alone without a home. Even isolated galaxies are not entirely alone. Many are accompanied by smaller satellite galaxies, which orbit them in slow, elliptical paths. Some of these satellites are gradually pulled apart by gravitational forces, their stars merging into the larger galaxy over time. The Milky Way, for example, is currently consuming several of its satellite galaxies, including the Sagittarius dwarf galaxy, whose stars are being stretched into a long tidal stream across the sky. This process of galactic cannibalism is a fundamental mechanism of growth, as larger galaxies absorb smaller ones, building themselves up over billions of years. Yet, for all their movement, galaxies appear almost frozen to the human eye, their motions playing out on timescales far beyond our own lifetimes. The stars and nebulae we see today have already shifted from their positions, but the changes are too gradual for us to perceive directly. Only through deep astronomical observations, spanning decades and centuries, can we detect the slow drift of galaxies across the heavens. As our telescopes become more advanced, we continue to map the motion of galaxies with increasing precision, uncovering the hidden forces that guide their paths. The James Webb Space Telescope and other observatories are revealing new insights into the early history of galactic movement, helping us understand how galaxies formed, evolved, and continue their cosmic journeys. In the end, the movement of galaxies is a reminder of the dynamic nature of the universe. Though they seem like distant, unchanging beacons in the night sky, they are constantly shifting, orbiting, and colliding silent travelers in an ever-expanding cosmos. Each galaxy is a floating island, a world unto itself, journeying through the infinite sea of space, following a path set in motion billions of years ago, yet still unfolding before our eyes. The universe, vast and immeasurable, is not static, it is expanding. Slowly, steadily, and imperceptibly on human timescales, space itself is stretching, carrying galaxies ever farther apart. This expansion is one of the most fundamental discoveries in modern cosmology, revealing the dynamic nature of the cosmos and reshaping our understanding of reality. Unlike explosions that radiate outward from a central point, the universe's expansion is uniform, occurring everywhere at once. It is not the galaxies themselves that are moving through space, but rather space itself that is growing, stretching the fabric of reality in all directions. The evidence for this expansion was first observed in the 1920s, when astronomers noticed that distant galaxies appeared to be receding from us. The further away a galaxy was, the faster it seemed to be moving. This phenomenon, known as redshift, occurs because light waves are stretched as space expands, shifting them toward the red end of the spectrum. This discovery, made by Edwin Hubble, provided the first solid proof that the universe was not eternal and unchanging, but rather evolving over time. Though the expansion may sound dramatic, it unfolds at an astonishingly slow pace, at least on the scale of human experience. If we could stand still and watch a distant galaxy, its movement would be imperceptible, shifting only by minuscule amounts over thousands or even millions of years. The speed of expansion is measured by the Hubble constant, which suggests that galaxies move away from each other by roughly 70 kilometers per second per megaparsec. This means that for every million parsecs, about 3.26 million light-years of distance, the recession speed increases by 70 kilometers per second. While this sounds fast, the sheer scale of cosmic distances makes the change almost unnoticeable on human timescales. The expansion is not uniform everywhere. While the large-scale universe stretches, galaxies within gravitationally bound clusters remain held together by their mutual attraction. The Milky Way, for instance, is not drifting away from the Andromeda galaxy. Instead, the two are on a collision course due to their local gravitational pull. Similarly, within galaxy clusters, individual galaxies orbit each other, largely unaffected by the overall expansion of space. The stretching of space is most apparent on the grandest scales, where entire clusters of galaxies recede from one another over billions of years. The exact nature of this expansion remains one of the deepest mysteries in cosmology. Observations suggest that the rate of expansion is not constant but accelerating. This discovery, made in the late 1990s, was unexpected. Scientists had assumed that gravity would gradually slow the expansion over time, yet the opposite was observed. Distant galaxies were moving away at an increasing rate. The force behind this acceleration is known as dark energy, a mysterious and unseen influence that makes up roughly 68% of the universe. Unlike normal energy or matter, dark energy does not clump together. Instead, it appears to be woven into the very fabric of space, pushing it outward with an ever-growing force. As time passes, this slow expansion will reshape the universe in profound ways. Billions of years from now, galaxies beyond our local group will drift so far away that their light will no longer be visible. The universe will appear darker and emptier, with distant stars and galaxies receding beyond the horizon of what we can observe. The cosmic web that now connects galaxies will thin out, and only the closest galaxies, bound together by gravity, will remain visible in the night sky. Yet, despite this slow and inevitable drift, the expansion of the universe does not affect everyday life. At local scales within galaxies, solar systems, and even atoms, other forces, such as gravity and electromagnetism, are far stronger than the gentle stretching of space. Planets continue to orbit their stars, stars continue to shine, and life continues to evolve, unaffected by the silent expansion of the cosmos. The fate of the universe remains an open question. If dark energy continues to accelerate expansion indefinitely, the universe may experience a big freeze, where galaxies drift apart so much that star formation ceases and the cosmos grows cold and dark. Some theories suggest a big rip, where the expansion becomes so extreme that it eventually tears apart galaxies, stars, and even atoms themselves. Others propose that expansion might slow or reverse one day, leading to a big crunch, where the universe collapses back in on itself. For now, the universe expands in a slow, graceful unfolding of cosmic time. It is a process too vast to perceive in a single lifetime, yet its effects shape the destiny of everything we see. The stars, the galaxies, and even the empty spaces between them are all part of this grand, continuous motiona, gentle stretching of the cosmos that has been happening for billions of years, and will continue long after the last star has faded from the sky. In the distant future, far beyond the lifespan of our own civilization, the universe will look vastly different from what we see today. As the cosmos continues its slow and steady expansion, the brilliant lights of countless stars will begin to fade, and the night sky will transform into something eerily quiet and dark. The universe, which once burned with the energy of countless galaxies, will drift toward a cold and silent fate. What will remain in this far future? How will the last stars of the universe endure? And what will they leave behind? The process of stellar evolution has been ongoing for billions of years, with stars forming from massive clouds of gas and dust, burning brightly for millions to billions of years, and then dying in spectacular supernovae or slow, quiet fades. However, the stars we see today are only a fraction of those that have existed. Many have already perished, and as time marches forward, fewer and fewer new stars will be born to replace them. In the universe's current era, the formation of stars continues in galaxies rich with gas and dust. However, this supply is not infinite. Over time, as galaxies continue to evolve, their reservoirs of star-forming material will deplete. The biggest and brightest stars, which burn through their fuel quickly, will vanish first. These massive stars, many of which are at least 10 times the mass of our own star, exhaust their hydrogen supply within a few million years, exploding in supernovae and leaving behind neutron stars or black holes. Their remnants persist, but they no longer shine with the light that once illuminated the universe. Smaller, long-lived star-sized dwarfs will survive far longer. These stars, much cooler and dimmer than those like our own, burn their hydrogen fuel at an extremely slow rate, allowing them to persist for trillions of years. In fact, many of the red dwarfs that formed shortly after the Big Bang are still shining today, and they will continue to do so long after larger stars have disappeared. But even their longevity is not infinite. Eventually, red dwarfs will exhaust their fuel, cooling and dimming into dark, lifeless husks known as black dwarfs. These objects will no longer emit light, blending into the background of an increasingly dark universe. As the eons pass, the galaxies themselves will undergo dramatic transformations. With fewer stars to illuminate them, they will become vast collections of stellar remnants, black holes, neutron stars, white dwarfs, and the cooling remains of what were once vibrant suns. Collisions between galaxies will become rare as the accelerating expansion of space-time pushes them apart. Eventually, galaxies beyond our local group will drift so far away that their light will never reach us again. The universe will become a place of isolated islands, with each remaining galaxy locked in solitude, its remaining stars fading away. At this stage, the only sources of energy in the universe will be the slow cooling of dead stars and the occasional collisions of stellar remnants. Black holes, the remnants of the most massive stars, will continue to exist, pulling in any remaining matter and merging with other black holes over time. Some will release bursts of energy in the form of Hawking radiation, a theoretical process in which black holes slowly evaporate over quadrillions of years. However, this radiation is incredibly faint, and even the most powerful black holes will eventually shrink and vanish into nothingness. The last true stars will be the smallest, faintest, and most fuel-efficient red dwarfs, burning at a fraction of the brightness of our own. As they reach the end of their lifespans, they will transition into white dwarf-shot, dense remnants of their former selves. White dwarfs are incredibly stable and will take trillions of years to cool down. Over time, they will fade into black dwarfs, cold and invisible to the naked eye. With no new stars forming and no more fusion taking place, the universe will enter its final phase zone dominated by darkness and decay. In this era, known as the degenerate era, matter itself will be all that remains. Planets, if they still exist, will be frozen wastelands orbiting dead stars, with no warmth or light to sustain them. The night sky, once filled with the brilliance of billions of galaxies, will be almost completely dark. The faint glow of distant white dwarfs and the occasional flicker of a decaying black hole will be the only sources of illumination. This phase of the universe will last for an unimaginable length of time. Trillions upon trillions of years will pass before even the last white dwarfs cool completely. But eventually, the universe will reach a state where nothing remains but black holes and dark, inert matter. In this final age, even black holes will evaporate, their last traces of radiation fading into the cold emptiness of space. The end result is what some physicists call the heat death of the universe, a state where no usable energy remains, and the cosmos exists in a motionless, featureless state of absolute darkness. There will be no stars, no galaxies, and no way to reverse the process. The universe, once filled with unimaginable energy and life, will be a vast, silent void. Yet, even in this bleak vision of the distant future, the story of the cosmos remains awe-inspiring. It is a testament to the passage of time on the grandest scale, a reminder that all things, no matter how brilliant, must eventually fade. The stars that shine today, the galaxies that fill the heavens, and even the universe itself are part of a grand cycle, one that stretches beyond the limits of human comprehension. For now, we exist in an age of light, where the night sky is filled with the glow of countless stars. The cosmos is still young compared to the eternity that awaits it. As we gaze up at the stars, we witness the universe in its premier moment of brilliance, in an unfathomable expanse of time. And while the future may be dark, the story of the universe is one of incredible wonder, reminding us that we are part of something vast, fleeting, and truly extraordinary. In the distant future, far beyond the lifespan of our own civilization, the universe will look vastly different from what we see today. As the cosmos continues its slow and steady expansion, the brilliant lights of countless stars will begin to fade, and the night sky will transform into something eerily quiet and dark. The universe, which once burned with the energy of countless galaxies, will drift toward a cold and silent fate. What will remain in this far future? How will the last stars of the universe endure? And what will they leave behind? The process of stellar evolution has been ongoing for billions of years, with stars forming from massive clouds of gas and dust, burning brightly for millions to billions of years, and then dying in spectacular supernovae or slow, quiet fades. However, the stars we see today are only a fraction of those that have ever existed. Many have already perished, and as time marches forward, fewer and fewer new stars will be born to replace them. In the universe's current era, the formation of stars continues in galaxies rich with gas and dust. However, this supply is not infinite. Over time, as galaxies continue to evolve, their reservoirs of star-forming material will deplete. The biggest and brightest stars, which burn through their fuel quickly, will vanish first. These massive stars, many of which are at least 10 times the mass of our own star, exhaust their hydrogen supply within a few million years, exploding in supernovae and leaving behind neutron stars or black holes. Their remnants persist, but they no longer shine with the light that once illuminated the universe. Smaller, long-lived stars, dwarfs, will survive far longer. These stars, much cooler and dimmer than those like our own, burn their hydrogen fuel at an extremely slow rate, allowing them to persist for trillions of years. In fact, many of the red dwarfs that formed shortly after the Big Bang are still shining today, and they will continue to do so long after larger stars have disappeared. But even their longevity is not infinite. Eventually, red dwarfs will exhaust their fuel, cooling and dimming into dark, lifeless husks known as black dwarfs. These objects will no longer emit light, blending into the background of an increasingly dark universe. As the eons pass, the galaxies themselves will undergo dramatic transformations. With fewer stars to illuminate them, they will become vast collections of stellar remnants, black holes, neutron stars, white dwarfs, and the cooling remains of what were once vibrant suns. Collisions between galaxies will become rare as the accelerating expansion of space-time pushes them apart. Eventually, galaxies beyond our local group will drift so far away that their light will never reach us again. The universe will become a place of isolated islands, with each remaining galaxy locked in solitude, its remaining stars fading away. At this stage, the only sources of energy in the universe will be the slow cooling of dead stars and the occasional collisions of stellar remnants. Black holes, the remnants of the most massive stars, will continue to exist, pulling in any remaining matter and merging with other black holes over time. Some will release bursts of energy in the form of Hawking radiation, a theoretical process in which black holes slowly evaporate over quadrillions of years. However, this radiation is incredibly faint, and even the most powerful black holes will eventually shrink and vanish into nothingness. The last true stars will be the smallest, faintest, and most fuel-efficient red dwarfs, burning at a fraction of the brightness of our own. As they reach the end of their lifespans, they will transition into white dwarf-shot, dense remnants of their former selves. White dwarfs are incredibly stable and will take trillions of years to cool down. Over time, they will fade into black dwarfs, cold and invisible to the naked eye. With no new stars forming and no more fusion taking place, the universe will enter its final phase zone dominated by darkness and decay. In this era, known as the degenerate era, matter itself will be all that remains. Planets, if they still exist, will be frozen wastelands orbiting dead stars, with no warmth or light to sustain them. The night sky, once filled with the brilliance of billions of galaxies, will be almost completely dark. The faint glow of distant white dwarfs and the occasional flicker of a decaying black hole will be the only sources of illumination. This phase of the universe will last for an unimaginable length of time. Trillions upon trillions of years will pass before even the last white dwarfs cool completely. But eventually, the universe will reach a state where nothing remains but black holes and dark, inert matter. In this final age, even black holes will evaporate, their last traces of radiation fading into the cold emptiness of space. The end result is what some physicists call the heat death of the universe, a state where no usable energy remains, and the cosmos exists in a motionless, featureless state of absolute darkness. There will be no stars, no galaxies, and no way to reverse the process. The universe, once filled with unimaginable energy and life, will be a vast, silent void. Yet, even in this bleak vision of the distant future, the story of the cosmos remains awe-inspiring. It is a testament to the passage of time on the grandest scale, a reminder that all things, no matter how brilliant, must eventually fade. The stars that shine today, the galaxies that fill the heavens, and even the universe itself are part of a grand cycle, one that stretches beyond the limits of human comprehension. For now, we exist in an age of light, where the night sky is filled with the glow of countless stars. The cosmos is still young compared to the eternity that awaits it. As we gaze up at the stars, we witness the universe in its premier moment of brilliance, in an unfathomable expanse of time. And while the future may be dark, the story of the universe is one of incredible wonder, reminding us that we are part of something vast, fleeting, and truly extraordinary. The universe, vast and boundless, stretches beyond the limits of human comprehension. As we peer into the night sky, we are greeted by the light of countless stars, each one a distant beacon from a different era of cosmic history. But beyond what we can see, beyond the furthest galaxies, lies an expanse so immense that it defies all attempts at measurement. The very concept of an infinite universe raises profound questions. Does space truly go on forever? Is there an edge to existence? And if so, what lies beyond? The observable universe, the portion of the cosmos that we can see, is dictated by the speed of light and the age of the universe itself. Since light travels at a finite speed, we can only detect objects whose light has had enough time to reach use approximately 13.8 billion years. However, due to cosmic expansion, the true size of the observable universe is estimated to be around 93 billion light-years across. But this is merely a fraction of the whole. Beyond this limit, galaxies continue to exist, their light simply unable to reach us yet. The universe does not end where our vision fades. It extends indefinitely into the unknown. One of the great mysteries of modern cosmology is whether the universe is truly infinite, or merely so large that we cannot perceive its boundaries. Some theories suggest that space may be curved in a way that allows it to loop back onto itself, meaning that if one were to travel in a straight line for an unimaginably long distance, they might eventually return to their starting point. Others propose that space is flat and extends without limit in all directions, forever expanding into an endless void. The idea of an infinite universe raises mind-bending possibilities. If space goes on forever, then it follows that every possible configuration of matter must eventually exist somewhere. There could be an infinite number of galaxies, an infinite number of stars, and perhaps even an infinite number of Earth-like planets. Some physicists speculate that, in such an expanse, there could be regions of space where the arrangement of atoms is identical to our own, meaning that somewhere, impossibly far away, an exact copy of you might be reading this very sentence. As we explore the infinite mysteries of the universe, we encounter another perplexing question. If space has no end, does time? The universe has been expanding since the Big Bang, and this expansion shows no signs of stopping. In fact, observations of distant galaxies reveal that they are accelerating away from us, driven by a mysterious force known as dark energy. If this acceleration continues indefinitely, the universe will grow ever larger, its galaxies drifting further apart until the night sky eventually becomes empty, devoid of the bright points of light we see today. Alternatively, some theories suggest that the universe may one day experience a reversal, an event known as the Big Crunch, where cosmic expansion slows and eventually contracts, leading to a collapse into a singularity, potentially triggering another Big Bang. Others speculate that the universe could be part of an endless cycle of expansion and contraction, an eternal rebirth of cosmic creation and destruction. Still, there remains the possibility that space will continue to exist forever, its galaxies spreading out into the infinite void, never to interact again. Beyond the vast distances and cosmic timescales, the concept of infinity raises philosophical and existential questions. If the universe has no end, what does that mean for our place within it? In an infinite cosmos, our planet, our lives, and even our entire galaxy might seem insignificant. But at the same time, the vastness of the universe serves as a reminder of the limitless potential for discovery. Each star, each galaxy, and each hidden corner of space represents a mystery waiting to be uncovered. The very fact that we can contemplate the nature of the universe is a testament to our curiosity and our drive to understand the unknown. The idea of a universe without an end is both humbling and exhilarating. It suggests that no matter how much we learn, there will always be more to explore, more to discover, and more mysteries to unravel. Whether space is truly infinite or merely so vast that we cannot perceive its boundaries, one thing remains certain: the universe will continue to challenge our understanding, inviting us to look beyond what we know and into the endless possibilities that lie ahead. Black holes, the enigmatic titans of the cosmos, shape the universe in ways both subtle and dramatic. Though they remain shrouded in darkness, their gravitational influence sculpts the galaxies, orchestrates the movements of stars, and even plays a role in the formation of new celestial structures. These silent behemoths, formed from the remnants of massive stars or emerging at the hearts of galaxies, are fundamental to the evolution of the universe. Despite their fearsome reputation as cosmic devourers, black holes are more than just destructive forces. They are the quiet architects of cosmic order. At the heart of nearly every large galaxy lies a supermassive black hole, millions or even billions of times the mass of a typical star. These colossal objects exert an immense gravitational pull, anchoring their galaxies and regulating the motion of billions of stars. Without them, the delicate balance that keeps galaxies intact might be disrupted, potentially leading to chaotic and unstable stellar environments. By exerting this quiet but unrelenting gravitational influence, black holes play a vital role in shaping the structure of the universe itself. Beyond holding galaxies together, black holes are also key players in the process of galaxy evolution. As matter falls toward a black hole, it forms an accretion disk, a swirling ring of superheated gas and dust that emits enormous amounts of energy. This process can generate powerful outflows, known as relativistic jets, which shoot vast amounts of energy and matter into intergalactic space. These jets can stretch for thousands of light years, influencing star formation by either triggering the collapse of gas clouds or dispersing them, thereby preventing new stars from forming. This delicate balance determines how and where stars emerge, shaping the future of entire galaxies. Black holes also influence the formation and fate of planetary systems. When massive stars collapse into black holes, the violent explosions that accompany this process supernovae release heavy elements essential for planet formation. Many of the elements that make up Earth, including carbon, oxygen, and iron, originated in the nuclear furnaces of massive stars and were later spread throughout space by such cataclysmic events. In this way, black holes indirectly contribute to the conditions necessary for the formation of planets and possibly life itself. On an even grander scale, the interaction of black holes can help explain the large-scale structure of the universe. When galaxies collide, their central black holes often merge in spectacular events, releasing enormous amounts of gravitational waves that ripple through the fabric of space-time. These mergers help shape the distribution of matter in the universe, influencing the growth of galactic clusters and cosmic filaments, the vast web-like structures that define the large-scale organization of galaxies. Despite their immense influence, black holes remain some of the most elusive objects in the cosmos. Because they do not emit light, they are only detectable through their interactions with nearby matter. However, advances in observational astronomy, including gravitational wave detection and high-resolution imaging, have allowed scientists to study black holes with unprecedented precision. The first direct image of a black hole's event horizon, captured in 2019 by the Event Horizon Telescope, provided a glimpse into the extreme physics governing these objects and confirmed predictions made by Einstein's general theory of relativity over a century ago. While black holes are often perceived as cosmic voids that consume everything in their path, they are in fact essential to the structure and evolution of the universe. They regulate the growth of galaxies, influence the formation of stars and planets, and even shape the very fabric of space itself. Though they work silently, their effects are profound and far-reaching. As our understanding of black holes deepens, so too does our appreciation for their quiet yet monumental role in shaping the cosmos. In the grand orchestration of the universe, black holes serve as both conductors and sculptors, shaping the past, present, and future of the celestial realms. Time, as we experience it, moves steadily forward, ticking away at a constant rate in our everyday lives. However, near a black hole, time behaves in ways that defy intuition. The immense gravitational pull of these cosmic giants warps the very fabric of space and time, creating an environment where time slows dramatically. This effect, known as gravitational time dilation, is one of the most astonishing predictions of Einstein's general theory of relativity. Near the event horizon of a black hole, time does not simply slow, it drifts almost to a standstill compared to the flow of time for a distant observer. To understand this phenomenon, one must first grasp the nature of gravity's effect on time. In Einstein's view, gravity is not merely a force pulling objects together, it is a curvature of space-time caused by massive objects. The stronger the gravitational field, the more extreme this warping becomes. Near the surface of the Earth, time already moves slightly slower compared to regions further from our planet's gravity. This effect is minuscule but measurable, and is accounted for in technologies such as GPS satellites, which must adjust for the tiny differences in time experienced at different altitudes. However, near a black hole, this effect becomes profoundly more pronounced. As an object falls toward a black hole, an outside observer would see its motion slow dramatically as it nears the event horizon, the boundary beyond which nothing can escape. From the perspective of this distant observer, the object would appear to move slower and slower, taking an infinite amount of time to actually reach the event horizon. However, for the object itself, time continues to flow normally. If an astronaut were to venture near a black hole's event horizon and somehow return, they would experience a vastly different passage of time compared to their colleagues who remained at a safe distance. While the astronaut might feel as if only a few moments or hours had passed, those outside the black hole's influence might have experienced decades, centuries, or even millennia. One of the most extreme examples of this phenomenon occurs near supermassive black holes giants that can be millions or even billions of times the mass of a typical star. In such environments, the time dilation effect is so intense that a single hour near the event horizon could correspond to thousands of years in a distant observer's reference frame. This idea has been popularized in science fiction, most notably in films like Interstellar. where astronauts visiting a planet near a black hole return to find that decades have passed for their colleagues in orbit. Beyond the event horizon, time takes on an even stranger character. According to our current understanding of physics, once an object crosses the event horizon, it is no longer part of the observable universe. The warping of space-time is so extreme that all paths lead inevitably toward the singularity, the infinitely dense point at the black hole's center. For an observer falling into a black hole, time might seem to flow normally at first, but as they approach the singularity, all known laws of physics break down, making it impossible to predict exactly what would be experienced. The implications of gravitational time dilation extend beyond black holes. It provides a glimpse into the fundamental nature of time itself, suggesting that time is not a fixed, universal quantity, but rather something that can stretch and compress depending on gravitational forces. This phenomenon has also led physicists to explore concepts such as time travel and wormholes, hypothetical tunnels through space-time that could, in theory, allow travel between distant points or even different times. While these ideas remain speculative, the reality of time dilation near black holes confirms that time is far more flexible than our everyday experience suggests. Black holes, in their silent, enigmatic nature, hold within them the keys to some of the deepest mysteries of the cosmos. The slow drift of time near these objects is not merely a theoretical curiosity. It is a real and measurable consequence of the universe's underlying structure. As we continue to study these fascinating celestial bodies, we move closer to unlocking the secrets of time itself, one of the most fundamental and elusive aspects of our reality. The question of whether extraterrestrial beings and civilizations exist has fascinated humanity for centuries. Given the vastness of the universe containing billions of galaxies, each with billions of stars and potentially even more planets, it seems increasingly unlikely that Earth is the only world to harbor life. The search for extraterrestrial intelligence, SETI, and ongoing discoveries of exoplanets in the habitable zones of their stars suggest that life may be more common than previously thought. However, whether advanced civilizations exist and whether they have attempted contact with us remains one of the greatest mysteries of modern science. Scientists approach the question of extraterrestrial civilizations through a variety of lenses, including astrobiology, astronomy, and even philosophy. One of the most well-known frameworks for assessing the likelihood of intelligent life is the Drake equation, formulated by astronomer Frank Drake in 1961. This equation estimates the number of active, communicative extraterrestrial civilizations within the Milky Way, taking into account factors such as the rate of star formation, the fraction of those stars with planets, and the likelihood of those planets developing life, intelligence, and technological capability. While the exact values of these parameters remain uncertain, recent exoplanet discoveries have made it clear that many stars host planetary systems, some of which may be capable of sustaining life. Despite these possibilities, the universe appears eerily silent. This paradox is known as the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" Given the age of the universe and the potential for civilizations to develop interstellar travel, one might expect that we would have already detected evidence of extraterrestrial intelligence. Numerous hypotheses have been proposed to explain this silence, ranging from the idea that intelligent civilizations self-destruct before they reach interstellar capability, to the possibility that extraterrestrials deliberately avoid contact with us. One of the primary ways scientists search for extraterrestrial civilizations is through the analysis of radio signals. Projects like the SETI Institute have scanned the cosmos for decades, hoping to detect artificial signals that may indicate an advanced intelligence. Although no definitive signals have yet been found, discoveries such as the mysterious WOW signal in 1977 have fueled speculation that intelligent life could be trying to communicate. Additionally, Advancements in optical and infrared telescopes have enabled scientists to search for potential signs of extraterrestrial technology, such as megastructures orbiting distant stars. Beyond scientific inquiry, the possibility of extraterrestrial life has also permeated human culture, inspiring countless books, films, and television series. From ancient myths of sky gods to modern depictions of interstellar travelers, humanity has long speculated about beings from beyond Earth. While fictional accounts often portray extraterrestrials as either benevolent explorers or hostile invaders, the reality, should we ever make contact, may be far more complex. If intelligent extraterrestrial civilizations exist, the implications for humanity would be profound. Contact with an advanced civilization could revolutionize our understanding of science, technology, and even our place in the universe. It could also raise ethical and existential questions about how we should interact with such beings. Would they be peaceful, or would they see us as competition? Would we be able to understand their language and motives? These questions remain purely hypothetical, but they highlight the profound impact that such a discovery could have. For now, the search for extraterrestrial beings and civilizations continues, with new missions, such as the James Webb Space Telescope, capable of analyzing the atmospheres of distant exoplanets for potential biosignatures, and the development of more sophisticated radio telescopes. Our ability to detect alien life is constantly improving. Whether we are alone or part of a vast cosmic community remains unknown, but the pursuit of this knowledge is one of the most exciting scientific endeavors of our time. As we explore the cosmos, we may one day find the answer to one of humanity's oldest and most profound questions. Are we alone? The universe is vast beyond comprehension, stretching across distances so immense that even the speed of light, the fastest thing in existence, takes billions of years to traverse it. The observable universe, the region of space from which light has had time to reach us since the beginning of cosmic time, is estimated to be about 93 billion light-years in diameter. This means that the light from the most distant galaxies we can see has traveled for roughly 13.8 billion years. But due to the continuous expansion of space, those galaxies are now much farther away than 13.8 billion light-years. One of the fundamental aspects of our universe is its expansion. Space itself is stretching, causing galaxies to drift apart from each other. This was first discovered by Edwin Hubble in the early 20th century when he observed that distant galaxies are moving away from us in all directions, with their light redshifted due to this expansion. This led to the understanding that the universe originated from a single, incredibly dense and hot point in what we now call the Big Bang. However, this expansion is not slowing down, it is accelerating due to a mysterious force known as dark energy. As a result, some parts of the universe are receding from us so rapidly that their light will never reach us, placing them forever beyond our observational horizon. The observable universe is not the same as the total universe. There is no reason to believe that what we can see is the full extent of reality. Based on cosmic inflation theory, a model that describes the universe's rapid expansion in the first fraction of a second after the Big Bang, many scientists believe that the universe could be at least hundreds of times larger than what is observable, possibly even infinite. If the universe is infinite, then no matter how powerful our telescopes become, we will always see only a fraction of its entirety. The sheer scale of the universe is staggering. Within the observable universe alone, there are an estimated 2 trillion galaxies, each containing hundreds of billions of stars. Around these stars orbit countless planets, some of which may harbor conditions suitable for life. Our own galaxy, the Milky Way, is just one of these countless star systems, measuring around 100,000 light-years across. Even at the speed of light, it would take 100,000 years to cross just our galaxy alone, and yet it is a mere speck in the grand scale of the cosmos. Beyond the sheer number of galaxies and stars, the structure of the universe itself is a complex web of matter and energy. Galaxies are not evenly distributed, but are arranged in vast clusters, superclusters, and cosmic filaments separated by enormous voids, where almost no matter exists. This large-scale structure gives the universe a breathtaking complexity that scientists are only beginning to understand. The immense distances between galaxies mean that interactions between them occur over billions of years, leading to collisions, mergers, and the formation of new stellar systems. Despite the mind-boggling size of the universe, our understanding is still limited. Some theories suggest the possibility of a multiverse, where our universe is just one of many. Others speculate that space might curve back onto itself, forming a cosmic loop where traveling far enough in one direction might eventually bring you back to your starting point. While these ideas remain theoretical, they highlight the fact that the universe's true nature is still one of the greatest mysteries in science. As technology advances, new telescopes like the James Webb Space Telescope allow us to peer deeper into space than ever before, capturing light from galaxies that formed just a few 100 million years after the Big Bang. Future observatories may push these limits even further, revealing more about the structure and origins of the universe. However, no matter how much we discover, the vastness of the cosmos ensures that there will always be more beyond our reach, waiting to be understood. The size of the universe is not just a question of measurement. It is a profound reminder of our place in the grand expanse of existence. In the face of such immense scale, our planet is a tiny oasis of life, a fragile world orbiting an ordinary star in the outskirts of a vast galaxy. Yet, despite our smallness, we are capable of understanding and exploring the universe, seeking answers to the fundamental questions of our origin and destiny. The journey of discovery continues, and with each new breakthrough, we take another step toward unraveling the ultimate mysteries of the cosmos. Looking even further, the question of what lies beyond the observable universe remains one of the most intriguing mysteries. If the universe is infinite, then it contains an uncountable number of galaxies, stars, and planets, perhaps even other civilizations that we have yet to detect. If it is finite but unbounded, then the curvature of space might cause light to bend in ways that could eventually reveal more about its true shape. Some physicists suggest that there might be entirely separate realms, or pocket universes, created by quantum fluctuations during cosmic inflation, each with its own distinct physical laws and constants. As our understanding of physics and cosmology deepens, we may one day develop new methods of exploring the farthest reaches of the universe, whether through advances in theoretical physics, new technologies that allow us to detect signals from distant civilizations, or even concepts like wormholes and warp drives. The future of space exploration is filled with infinite possibilities. While we may never truly grasp the full scope of the universe, our quest to understand it is a testament to human curiosity and the desire to explore the unknown. The Milky Way galaxy is an immense and complex structure, a vast cosmic city of stars, gas, dust, and dark matter stretching across a staggering distance of approximately 100,000 to 200,000 light-years in diameter. This means that even if you could travel at the speed of light about 300,000 kilometers per second, 186,000 miles per second, it would still take 100,000 to 200,000 years to traverse from one end of our galaxy to the other. However, recent studies suggest that the Milky Way might be even larger than previously estimated, extending further into the darkness of space. Some estimates suggest the outskirts of the galaxy, including its dark matter halo, could stretch up to 1 million light-years across. At the heart of our galaxy lies Sagittarius A, a supermassive black hole weighing around 4 million times the mass of our star. This black hole exerts a powerful gravitational pull, anchoring the Milky Way's spiral structure. The galaxy itself is a barred spiral, meaning it has a central elongated bar of stars, from which sweeping spiral arms extend. These spiral arms contain vast star-forming regions, nebulae, and countless planetary systems. each with the potential to harbor life. The spiral arms themselves are not solid structures, but rather dynamic, rotating patterns of gas and stars shaped by gravitational interactions and density waves that trigger star formation. The Milky Way is composed of several major components. The galactic disk is where most of the stars, planets, and nebulae are found. It is about 1,000 light-years thick and filled with hundreds of billions of stars, including our own solar system, which is located about 27 light-years from the galactic center in one of the spiral arms known as the Orion Arm, or local arm. The disk is also home to vast clouds of gas and dust that serve as nurseries for new stars, creating brilliant nebulae that shine across the galaxy. It is estimated that, on average, one new star is born in the Milky Way every year. Surrounding the disk is the galactic halo, an enormous spherical region extending far beyond the visible stars. This halo contains ancient stars and mysterious dark matter, which makes up the majority of the galaxy's mass. Dark matter does not emit light or energy, yet its gravitational effects can be observed as it influences the motion of stars and galaxies. The halo also hosts globular clusters, which are tightly packed, ancient groups of stars, some of which are nearly as old as the universe itself. The Milky Way's halo extends well beyond the visible disk and contains many stars that were likely stolen from smaller galaxies in past mergers. The Milky Way is not isolated, it is part of a cosmic neighborhood known as the Local Group, a collection of more than 50 galaxies bound together by gravity. The two most notable members are the Andromeda Galaxy, M31, and the Triangulum Galaxy, M33. Andromeda is the largest galaxy in the Local Group and is on a slow collision course with the Milky Way. In about 4.5 billion years, these two massive galaxies will merge, creating an entirely new galaxy, sometimes referred to as Milkomeda by astronomers. Despite this collision, the vast distances between stars mean that direct stellar collisions will be extremely rare, but the gravitational interactions will drastically reshape the structure of both galaxies. One of the most intriguing aspects of our galaxy is its stellar population. The Milky Way contains an estimated 100 to 400 billion stars, ranging from massive blue supergiants to faint red dwarfs. Some of these stars host planetary systems, and based on recent exoplanet discoveries, it is likely that there are billions of Earth-like planets orbiting stars within our galaxy. Many of these worlds may harbor the right conditions for life, making the Milky Way a prime location for the search for extraterrestrial civilizations. Some of these planetary systems may have already witnessed the rise and fall of intelligent life over cosmic timescales. Beyond the vast number of stars and planets, the Milky Way is a constantly evolving structure. Over the course of billions of years, it has consumed smaller galaxies, incorporating their stars into its own structure. Even now, it continues to interact with dwarf galaxies, such as the Magellanic Clouds, which orbit the Milky Way and may eventually be absorbed into its mass. Streams of stars from past galactic mergers crisscross the Milky Way, providing clues about its tumultuous history of growth and interaction with other galaxies. The galaxy's motion is another fascinating aspect. The entire Milky Way is rotating at an average speed of 828,000 kilometers per h, 514,000 miles per hour. However, despite this rapid movement, a full rotation of the galaxy takes about 225 to 250 million years. To put that into perspective, the last time Earth was in the same position in the Milky Way's rotation, dinosaurs were just beginning to dominate the planet during the Triassic period. Meanwhile, the Milky Way itself is hurtling through space at over 2.1 million kilometers per h, 1.3 million miles per hour, being pulled toward a mysterious gravitational region known as the Great Attractor. Our galaxy is a breathtakingly vast and dynamic system, filled with mysteries yet to be unraveled. From its enormous size to its hidden dark matter, from its billions of stars to its ever-expanding arms, the Milky Way is a testament to the grandeur of the cosmos. It is a constantly changing, living entity shaped by the gravitational ballet of stars, dark matter, and galactic mergers. As our technology advances, new telescopes and observatories will continue to reveal more about the nature of our home galaxy, offering deeper insights into its past, present, and future. The Milky Way is not just our cosmic address, it is an evolving masterpiece of the universe, an island of stars adrift in the endless sea of space. The solar system is vast, spanning an almost incomprehensible distance, far beyond the familiar planets that orbit our star. While we often think of the solar system as ending with Neptune, its true extent stretches far beyond what the eye can see, into the depths of interstellar space. Measuring the solar system's size is not as simple as defining a clear boundary. Instead, astronomers use different markers to establish its limits, from the orbit of Neptune to the edge of the star's influence, known as the heliosphere, and even further to the hypothetical Oort cloud. The inner solar system consists of the terrestrial planets Mercury, Venus, Earth, and Mars, along with the asteroid belt that lies between Mars and Jupiter. This region is relatively compact, spanning a mere few 100 million kilometers. However, beyond this lies the outer solar system, home to the gas giants, Jupiter, Saturn, Uranus, and Neptune. These planets are spaced much farther apart, and the distance from the star to Neptune, the farthest known major planet, is about 4.5 billion kilometers, 2.8 billion miles. This distance is defined as 30 astronomical units, AU, where 1 AU is the average distance between Earth and the star, approximately 150 million kilometers, 93 million miles. Yet, even at Neptune's orbit, we are only scratching the surface of the solar system's vastness. Beyond Neptune lies the Kuiper Belt, a region filled with icy objects, dwarf planets like Pluto, Eris, and Makemake, and countless comets. The Kuiper Belt extends from about 30 AU to 50 AU, meaning it reaches up to 7.5 billion kilometers, 4.6 billion miles from the star. While the Kuiper Belt contains many fascinating objects, it is still within the star's gravitational grasp. Farther still lies the scattered disk, a sparsely populated region of icy bodies that extends beyond the Kuiper Belt, reaching distances of up to 100 AU or more. Objects in the scattered disk, such as the dwarf planet Sedna, follow elongated orbits that take them far away from the star for thousands of years before they swing back inward. Some of these objects could be influenced by the hypothetical Planet 9, a yet undiscovered world that might be lurking in the distant reaches of the solar system. However, the solar system does not end at the Kuiper Belt or the scattered disk. The true boundary of the solar system is often defined by the heliosphere, the vast bubble of charged particles and magnetic fields created by the star's solar wind. The heliosphere extends to about 120 AU from the star, where the solar wind slows down and interacts with the interstellar medium. This boundary is called the heliopause, and it represents the point where the star's influence starts to wane. The two Voyager spacecraft, launched in 1977, have traveled beyond this boundary, officially entering interstellar space. Voyager 1 crossed the heliopause in 2012, followed by Voyager 2 in 2018, making them humanity's farthest-reaching spacecraft. Beyond the heliopause lies the Oort cloud, an enormous and hypothetical region of icy bodies that is thought to surround the solar system like a giant, spherical shell. The Oort cloud is the birthplace of long-period comets, which take thousands or even millions of years to complete an orbit around the star. The Oort cloud's inner edge may begin around 2,000 to 5,000 AU, but its outer boundary is estimated to extend as far as 100,000 AU, 1.5 light-years from the star. This means that if the Oort cloud exists, it could reach about a quarter of the distance to the nearest star system, Proxima Centauri, which lies 4.24 light-years away. To put these distances into perspective, light, the fastest thing in the universe, takes 8 minutes to travel from the star to Earth. It takes over 4 hours to reach Neptune, over 17 hours to reach the heliopause, and over 1.5 years to reach the edge of the Oort cloud. If a spacecraft were to travel at the speed of Voyager 1, about 17 kilometers per second, 38,000 miles per hour, it would still take over 30,000 years to reach the Oort cloud's outer boundary. The solar system is not just a collection of planets orbiting a star, it is a vast and complex structure extending deep into interstellar space. Its true size is difficult to define, as its outermost regions gradually blend into the surrounding galaxy. While planets and moons make up the most familiar parts of the solar system, the vast emptiness that stretches beyond Neptune tells a story of our star's influence, reaching far and wide. The mysteries of the Oort cloud, the scattered disk, and the hypothetical Planet 9 remind us that even in our own cosmic backyard, much remains to be discovered. As technology advances and future missions push farther into deep space, we may one day map the true extent of the solar system, revealing just how immense and extraordinary our celestial home truly is. Gas giants are some of the most intriguing and awe-inspiring planets in our universe. These massive worlds, like Jupiter, Saturn, Uranus, and Neptune in our own solar system, are composed primarily of gases, such as hydrogen and helium, and lack solid surfaces like Earth or Mars. Gas giants are often characterized by their immense size, thick atmospheres, and numerous moons. The 4 gas giants in our solar system, Jupiter, Saturn, Uranus, and Neptune, are drastically different from the rocky planets that orbit our Sun. While the rocky planets are composed of metals and silicate rock, gas giants are made up of lighter elements that form dense atmospheres. These planets are also much larger, with masses that far exceed Earth's, and they exert massive gravitational pulls, which can have a significant impact on their moons and even the entire solar system. Jupiter, the largest planet in our solar system, is a true giant, with a diameter of around 139,820 kilometers. It could fit over 1,300 Earths inside it. The planet's atmosphere is primarily composed of hydrogen and helium, with a combination of ammonia, methane, and water vapor. Jupiter's Great Red Spot, a massive storm larger than Earth, has been raging for at least 400 years, making it one of the most striking features in the solar system. Saturn, the second largest gas giant, is famous for its stunning rings. These rings are made up of ice particles, rock fragments, and dust. Saturn's atmosphere, like Jupiter's, is mostly hydrogen and helium. The planet has over 80 moons, with Titan being the largest and most notable. Titan is the only moon in the solar system with a thick atmosphere, and it's often studied for its similarities to early Earth, with liquid lakes of methane and ethane. Uranus and Neptune, the ice giants, are often grouped with gas giants but have notable differences. These 2 planets contain more water, ammonia, and methane than Jupiter and Saturn, which gives them their blue appearance. Neptune, the farthest planet from the Sunday, has winds that can reach speeds of over 2,000 kilometers per hour, the fastest in the solar system. Uranus, on the other hand, is tilted at a bizarre 98-degree angle, possibly due to a massive collision early in its history. This unique tilt causes extreme seasons, with one pole facing the Sunday for decades at a time. Gas giants are not only fascinating because of their size and composition, but also due to their formation. These planets are thought to form in the outer regions of a star system, where temperatures are low enough for gases to condense and accumulate. During the formation of a gas giant, a solid core forms first, and then gravity pulls in surrounding gas and dust, creating the massive thick atmospheres we see today. In some cases, the gas giant may even prevent the formation of other planets by clearing out debris in its orbital path. The gas giants in our solar system have a profound influence on the other planets and objects that orbit the Sunday. Jupiter, for example, plays a critical role in shaping the orbits of asteroids in the asteroid belt. Its immense gravity can either fling asteroids toward the inner solar system or push them away, helping to protect the inner planets, including Earth, from potential asteroid impact. Beyond our solar system, astronomers have discovered thousands of exoplanets, many of which are gas giants or gas giant-like. These exoplanets, which orbit other stars, can vary dramatically in size, composition, and distance from their stars. Some are similar to the gas giants in our solar system, while others, like hot Jupiters, orbit much closer to their stars and experience extreme temperatures. The study of gas giants has expanded our understanding of planetary formation and the potential for habitable worlds. While gas giants themselves may not support life as we know it, their moons and rings offer exciting possibilities for future exploration. Moons like Titan and Europa, which orbit Saturn and Jupiter respectively, are thought to have subsurface oceans beneath their icy crusts, making them prime targets in the search for extraterrestrial life. In conclusion, gas giants are some of the most extraordinary and mysterious objects in the universe. Their massive size, thick atmospheres, and numerous moons make them both scientifically fascinating and visually stunning. As we continue to explore these distant worlds, we gain a better understanding of the formation of planetary systems and the potential for life beyond Earth. From their swirling storms to their icy moons, gas giants remain one of the most captivating subjects in the study of space. Dark matter is one of the greatest mysteries in the universe. It is something we cannot see, touch, or directly interact with. Yet it makes up about 27% of the universe's total mass and energy. Unlike normal matter, which includes stars, planets, and galaxies, dark matter does not emit, absorb, or reflect light. It is completely invisible, detectable only through its gravitational effect. For decades, scientists have been trying to understand what dark matter is, why it exists, and how it shapes the universe. Despite all our technological advancements, dark matter remains one of the most elusive components of the cosmos. The idea of dark matter dates back to the 1930s, when Swiss astronomer Fritz Zwicky made a surprising observation. He was studying a group of galaxies called the Coma Cluster and found that the galaxies within it were moving far too fast. According to Newtonian physics, if these galaxies were only influenced by visible matter, they should have been moving much slower, even flying apart. But something was holding them together, something invisible. Zwicky called this unseen mass, dunkle materie, or dark matter. His discovery was ignored for decades, but in the 1970s, American astronomer Vera Rubin found more compelling evidence. She was studying the rotation speeds of galaxies, expecting that the outer stars would move more slowly than the inner ones, just like planets in our solar system. Instead, she found that the outer stars were moving just as fast as those closer to the center. This made no sense unless there was some invisible mass surrounding the galaxy, exerting gravitational force. Scientists now believe that dark matter forms a sort of cosmic scaffolding, holding galaxies together and playing a crucial role in the structure of the universe. Without it, galaxies would not have enough mass to remain stable, and they would be torn apart by their own rotational speed. Even though we cannot see dark matter, its presence is felt everywhere. One of the strongest pieces of evidence for dark matter comes from gravitational lensing. This phenomenon occurs when the gravity of a massive object bends and distorts the light coming from more distant objects. When astronomers observe galaxy clusters, they find that the amount of lensing is far greater than what visible matter alone can account for. Something invisible is adding extra mass and bending the light even more than expected. Another major clue comes from the cosmic microwave background radiation, the faint afterglow of the Big Bang. This radiation provides a snapshot of the early universe and detailed measurements of it, especially from missions like WMAP and Planck, show that normal matter makes up only a small fraction of the total mass in the universe. The way galaxies and large-scale structures formed suggests there must have been a massive, unseen presence shaping them, another indirect confirmation of dark matter. Despite all this evidence, no one knows exactly what dark matter is made of. One leading theory suggests that dark matter consists of weakly interacting massive particles, or WIMPs. These hypothetical particles barely interact with normal matter, except through gravity, which would explain why they are so difficult to detect. If WIMPs exist, they should occasionally collide with normal matter in a way that could be observed in underground detectors. Scientists have built massive experiments, such as the Large Underground Xenon Lux detector and the Xenon 1T experiment, hoping to catch a glimpse of these elusive particles. So far, no direct detection has been made. Another possibility is that dark matter is made of axions, extremely light and weakly interacting particles that could explain some of the missing mass in the universe. These particles have yet to be observed, but ongoing experiments are searching for subtle effects they might produce in electromagnetic fields. There is also a more radical idea. What if dark matter is not made of particles at all? Some alternative theories suggest that our understanding of gravity itself might be incomplete. One such theory is modified Newtonian dynamics, MOND, which proposes that at extremely large cosmic scales, gravity behaves differently than we currently understand. While MOND can explain some galactic rotation curves, it struggles to account for all the evidence supporting dark matter, such as gravitational lensing and cosmic structure formation. The search for dark matter is one of the most active fields in physics today. Particle accelerators like the Large Hadron Collider are searching for new particles that could be candidates for dark matter. Space telescopes like the Fermi Gamma Ray Space Telescope are looking for indirect signals of dark matter interactions, such as excess gamma rays, that might be produced when dark matter particles collide and annihilate each other. Despite decades of searching, dark matter remains elusive. But the quest to understand it is pushing the boundaries of physics, leading to new insights into the nature of the universe. If dark matter is eventually detected and understood, it could revolutionize our understanding of fundamental physics, answering some of the biggest questions about the cosmos. The universe is still full of mysteries, and dark matter is one of the biggest ones. Every new discovery brings us closer to unlocking its secrets. And while we may not yet know what it is, its gravitational fingerprints are all around us. The answer to this cosmic riddle may be just around the corner, waiting to be uncovered. No one knows for sure what lies beyond the edge of the universe. The universe, as we know it, is vast, stretching across an estimated 93 billion light-years in diameter. Yet its true size could be far greater, even infinite. The observable universe is the portion we can see, limited by the speed of light and the age of the cosmos. But what lies beyond what we can observe? What exists past the farthest galaxies, past the cosmic horizon, beyond the very limits of our sight? To understand this, we first need to grasp what the edge of the universe actually means. There are two ways to think about it: the edge of the observable universe and the edge of the actual universe. The observable universe is simply the region from which light has had time to reach us since the Big Bang, about 13.8 billion years ago. Because space itself is expanding, the farthest galaxies we can detect are actually much farther than 13.8 billion light-years away, more like 46 billion light-years in any direction. Beyond this horizon, light from distant objects has not had enough time to reach us, making everything beyond it effectively invisible. But this does not mean nothing exists beyond that boundary. In fact, most cosmologists believe the universe continues far beyond what we can observe. The expansion of space means there could be countless more galaxies, structures, and possibly even new physics that we simply cannot see. The universe might extend forever, stretching endlessly into an infinite expanse of space. If that's the case, then no matter how far we travel, there would always be more stars, galaxies, and cosmic wonders beyond our reach. However, if the universe is not infinite, then it must have a shape, and if it has a shape, it could theoretically have an edge. Some models suggest the universe could be curved, like the surface of a sphere. In this scenario, if you traveled in one direction long enough, you might eventually end up back where you started, just as if you walked in a straight line on Earth. This means the universe could be finite, but unbounded it would have a limited volume but no true edge. Then there's the possibility of a true cosmic edge, where the fabric of space-time itself ends. If the universe is finite and has an edge, what happens there? One theory suggests that beyond the universe, there could be a vast, empty void, something completely devoid of space, time, and matter. In this case, the universe would be like an isolated bubble in a much larger, unknowable reality. Another mind-bending idea comes from the multiverse hypothesis. Some theories suggest that our universe is just one of many, like a single bubble floating in an infinite cosmic ocean filled with other universes. If this is true, then beyond the edge of our universe, there could be entirely different realities with different physical laws, different forms of matter, or even different dimensions. Some of these universes might be similar to ours, while others could be utterly alien, with physics so different that they are beyond human comprehension. The idea of parallel universes is supported by some interpretations of quantum mechanics, as well as theories like eternal inflation. According to this idea, the universe underwent a rapid expansion just after the Big Bang, and different regions of space may have inflated at different rates, creating separate pocket universes. If this is the case, then our observable universe is just one small part of a much larger cosmic multiverse. There's also the question of whether the universe is expanding into something. When we talk about the universe expanding, we are not saying that galaxies are moving through space into an already existing void. Instead, space itself is stretching, creating more space as it expands. This means that asking what's beyond the universe may not even be the right question, because there is no outside in the way we usually think of it. The universe isn't expanding into something else. Rather, it is expanding within itself. But what about the biggest question of all? Could we ever reach or see beyond the edge? The answer is almost certainly no. The expansion of the universe is accelerating due to dark energy, meaning the most distant galaxies are moving away from us faster than the speed of light. Any light they emit today will never reach us, effectively sealing off those regions forever. Even if we built the fastest spaceship imaginable, traveling at 99.9999% the speed of light, we could never catch up with the expanding edge of the universe. The further we go, the faster the space ahead of us is stretching away. This means that even if there is something beyond our universe, we may never know what it is. It remains one of the greatest mysteries in all of science. Is there an infinite expanse of galaxies stretching into eternity? Are there other universes waiting beyond a cosmic horizon? Or does the universe simply end, with nothing beyond it, no space, no time, no existence? For now, the edge of the universe is a boundary not just of space, but of human knowledge. But every new discovery in physics and cosmology brings us one step closer to unlocking the secrets of what lies beyond. The answers may change our entire understanding of reality itself. The universe is constantly changing, evolving over billions of years. Right now, galaxies are moving farther apart, stars are being born and dying, and the fabric of space itself is stretching. But what happens next? What will the universe look like in the next 100 billion years? As time moves forward, the expansion of the universe continues. Right now, the universe is growing at an accelerating rate due to the mysterious force known as dark energy. Over the next several billion years, galaxies will keep moving farther and farther apart. Those outside our local group, which includes the Milky Way, Andromeda, and a few dozen smaller galaxies, will drift away so fast that their light will no longer reach us. The universe beyond our local region will become invisible, fading into the blackness of space. Inside the local group, galaxies will still interact. Within the next few billion years, the Milky Way and Andromeda will collide, merging into a single, giant elliptical galaxy. The night sky will look very different. filled with new star systems formed from the chaos of this galactic merger. But despite this transformation, star formation across the universe will slow down. Stars are the engines of the cosmos, but they do not last forever. Over time, fewer new stars will form, and existing stars will begin to burn out. The largest stars will explode as supernovae, while medium-sized stars like the Sunday will swell into red giants before fading into white dwarfs. The smaller, cooler red dwarf stars, which are the most common in the universe, will last much longer, but even they will eventually fade away. After tens of billions of years, the universe will enter what some scientists call the degenerate era time, when star formation has mostly stopped, and only the remnants of old stars remain. White dwarfs will slowly cool into black dwarfs, objects so faint they will be nearly undetectable. Black holes will continue to grow, consuming any remaining matter around them. In the far future, galaxies will become dark and quiet, with only the faint glow of dying stars. Planets that once orbited vibrant suns will drift through space in total darkness. The universe will become a colder, emptier place. But even as stars fade, black holes will remain. Over time, they will slowly evaporate through a process called Hawking radiation, losing tiny amounts of mass until they eventually vanish. This process takes an incredibly long time, far beyond 100 billion years, but it marks the slow end of one of the last remaining sources of energy in the universe. As more time passes, the expansion of space may have even stranger effects. Some theories suggest that dark energy could become stronger over time, eventually leading to a scenario called the Big Rip. In this version of the future, space will expand so violently that galaxies, stars, planets, and even atoms themselves will be torn apart. If the Big Rip happens, the universe will end in complete destruction. However, if dark energy remains constant, the universe will continue expanding indefinitely. Over hundreds of billions of years, all remaining matter will become so spread out that interactions between particles will become extremely rare. The cosmos will approach heat death, a state where everything is so evenly distributed that no useful energy remains to power stars or galaxies. The universe will be cold, empty, and unchanging. But could something else happen? Some theories suggest the universe might not expand forever. It could go through cycles of expansion and contraction, eventually leading to a big crunch, where the universe collapses back in on itself, possibly leading to another Big Bang and the birth of a new universe. While this idea is intriguing, current evidence suggests the universe is likely to continue expanding forever. The future of the universe is a story of transformation, from a bright and active cosmos full of stars and galaxies to a dark, empty expanse. Over the next 100 billion years, the universe will grow larger, colder, and lonelier. Stars will fade, galaxies will disappear from view, and time itself will stretch on toward an uncertain fate. The end may come in darkness, or perhaps in ways we have yet to discover. The universe is vast, ever-changing, and incredibly old. But even with its age, we are only witnessing a tiny fraction of its entire lifetime. As time stretches forward, the cosmos will evolve in ways that are difficult to comprehend. What will the universe look like **** 100 trillion years from now? What will remain after all the stars have burned out, and will anything be left in the endless darkness? As the clock moves forward, the first major change is the continued expansion of the universe. Right now, galaxies are moving apart due to dark energy, and this process is accelerating. Over time, distant galaxies will drift so far away that their light will never reach us again. The only galaxies left within view will be the ones in our local group, a collection of galaxies that includes the Milky Way and Andromeda. Eventually, these galaxies will merge into a single, massive, elliptical galaxy. Inside this newly formed galaxy, stars will continue to be born, live their lives, and eventually die. But star formation is not infinite. The gas and dust needed to create new stars are slowly being used up. Over the next few trillion years, fewer and fewer new stars will emerge. The universe, once bright and filled with countless points of light, will start to go dark. The most massive stars will die first, burning through their fuel in just a few million years before exploding in supernovae, leaving behind black holes and neutron stars. Medium-sized stars, like the Sunday, will expand into red giants before shedding their outer layers and becoming white dwarfs, dim, slowly cooling remnants of what were once brilliant stars. But the real survivors of the universe are the red dwarfs. These small, dim stars burn their fuel at an incredibly slow rate, allowing them to last for trillions of years. While larger stars will have long since faded away, red dwarfs will continue to shine, keeping the universe from falling into total darkness. As we approach * 10 trillion years into the future, even the red dwarfs will begin to die. These stars do not explode in dramatic fashion like their larger counterparts. Instead, they simply burn out, cooling and fading, until they become black dwarfs, dark frozen remnants that emit no light. By the time we reach * 100 trillion years, the universe will have entered what is known as the degenerate era. No new stars will form. The last remaining sources of light will be the faint glow of cooling white dwarfs and the occasional flashes from supernovae triggered by the collision of stellar remnants. The universe will be much darker than it is today, a place dominated by cold, lifeless objects. At this point, galaxies will no longer look like the vibrant, swirling formations they once were. Instead, they will be filled with black holes, neutron stars, and black dwarfs, with no bright stars left to illuminate the darkness. Any planets that once orbited these stars will be drifting alone through space, frozen solid, with no sunlight to warm them. But even in this era of darkness, black holes remain. These strange objects, formed from the collapse of massive stars, will continue to exist for unimaginable periods of time. Over the next trillions and quadrillions of years, black holes will slowly merge with one another, creating supermassive black holes, even larger than the ones we see at the centers of galaxies today. Yet even black holes are not eternal. Over incredibly long timescales, they slowly lose mass through Hawking radiation, a process where tiny amounts of energy escape from their event horizons. Smaller black holes will vanish first, disappearing into bursts of radiation. The largest black holes, however, will take quintillions of years to evaporate completely. As time moves even further beyond * 100 trillion years, all normal matter stars, planets, and even black holes will eventually fade away. The universe will continue expanding, stretching space itself into an emptier and colder void. Any remaining particles, like protons, may begin to decay, breaking down into even smaller components. If proton decay happens, all remaining matter in the universe will eventually be reduced to a thin mist of subatomic particles spread across an ever-growing cosmos. At this stage, the universe will become a vast, featureless void, with no galaxies, no stars, and no black holes. The last remaining energy in the universe will be the faint radiation left over from black hole evaporation, slowly cooling to near absolute zero. But what happens next? Could this be the ultimate fate of the universe, or is there something beyond this era of nothingness? There are several possibilities for what might come after this dark future. One possibility is that the universe will continue expanding forever, eventually reaching a state known as heat death. In this scenario, the cosmos becomes completely uniform, with no remaining energy differences to drive any form of activity. There will be no stars, no movement, and no structures, just a silent, empty expanse that stretches endlessly in all directions. Another possibility is the Big Rip, in which dark energy continues to accelerate the expansion of the universe until it becomes so extreme that even atoms themselves are torn apart. If this happens, space itself will be ripped apart, leaving behind nothing at all. Alternatively, some theories suggest that the universe might undergo a big crunch, where gravity eventually overcomes expansion, pulling everything back together into a single point. If this happens, it could trigger another Big Bang, starting a new universe from scratch. However, current evidence suggests that the universe's expansion is only accelerating, making a big crunch unlikely. Some physicists propose a more exotic idea that new universes could be born from the remains of this one. Quantum fluctuations in the void of space could give rise to new Big Bangs, creating entirely new realities separate from our own. If this is true, then while our universe may fade into nothingness, the cycle of cosmic creation could continue elsewhere. But for now, as far as we can tell, the future of the universe is one of darkness and silence. Over the next 100 trillion years, all stars will burn out, all planets will freeze, and the cosmos will slowly fade into a cold, empty void. Whether this is truly the end or just another step in an endless cycle remains one of the greatest mysteries of all. How our solar system formed is a story that began billions of years ago, long before the Earth, the Sun, or even the planets existed. It is a tale of dust, gas, and cosmic forces coming together to create the world we live in today. To understand how it all happened, we must go back to a time when our solar system was nothing more than a vast, swirling cloud of gas and dust floating in space. About 4.6 billion years ago, a massive cloud of gas and dust, known as a nebula, existed in a quiet region of our Milky Way galaxy. This nebula was not unique among many. Such clouds exist throughout the universe, remnants of ancient stars that had exploded in supernovae. These clouds contain all the raw materials needed to form new stars and planets. For millions of years, this cloud floated in space, slowly moving and changing shape. But something happened that triggered a dramatic transformation. Scientists believe that a nearby supernova explosion may have been the catalyst. The powerful shockwave from this dying star sent ripples through the nebula, causing it to collapse in on itself. As the cloud began to shrink, gravity took over, pulling more and more material toward the center. As the cloud collapsed, it started to spin. Just like a figure skater pulling in their arms to spin faster, the collapsing cloud rotated more quickly as it shrank. At the heart of this spinning disk of gas and dust, matter was pulled together to form what would eventually become the sun. The pressure and temperature in the center of the collapsing cloud increased dramatically. Over time, the heat and pressure became so intense that nuclear fusion began a process where hydrogen atoms fused together to form helium, releasing an enormous amount of energy. At that moment, the sun was born, glowing brightly and sending out powerful radiation into space. But the formation of the sun was only the beginning. The rest of the material in the cloud still had to settle. And this is where the planets, moons, asteroids, and other objects in our solar system began to form. As the sun ignited at the center, the remaining gas and dust continued to spin around it, forming a protoplanetary disk. Within this disk, tiny dust particles began to stick together, forming larger and larger clumps. Over millions of years, these small clumps grew into planetesimals, objects that were large enough to attract more material through their own gravity. In the inner part of the solar system, where it was very hot, only certain types of materials could survive. Metals and rocky materials were able to withstand the heat, while lighter elements like hydrogen and helium were pushed farther out by the intense solar radiation. This is why the terrestrial planets, Mercury, Venus, Earth, and Mars are rocky and dense, while the gas giants Jupiter, Saturn, Uranus, and Neptune formed farther away, where it was cooler. As these planetesimals continued to collide and merge, they formed protoplanets, larger bodies that would eventually become the planets we know today. These growing worlds went through violent periods of impacts. where asteroids and other debris crashed into them. Some of these impacts were so powerful that they changed the planets forever. One of the most significant collisions happened to Earth. A massive object, roughly the size of Mars, slammed into our young planet, sending a huge amount of debris into space. Over time, this debris came together to form the Moon. This impact not only gave Earth its moon, but also helped shape our planet's atmosphere and rotation. Meanwhile, in the outer solar system, the gas giants were forming in a different way. Because they were farther from the Sun, they were able to collect massive amounts of gas from the surrounding nebula. Jupiter, the largest planet in our solar system, was the first to form. Its strong gravity allowed it to capture huge amounts of hydrogen and helium, making it a giant ball of gas. Saturn followed a similar process, while Uranus and Neptune formed farther out, where the material was even colder. As the planets took shape, the remaining dust and gas in the solar system started to clear away. The Sun's powerful solar wind stream of charged particles swept through the solar system, pushing away the remaining light gases and dust. Over time, only the planets, moons, asteroids, and comets remained. Even after the planets had fully formed, the solar system was still a chaotic place. Countless asteroids and comets were left over from the formation process, and many of them crashed into the planets. This period, known as the Late Heavy Bombardment, lasted for hundreds of millions of years. During this time, the Moon, Mercury, and other rocky bodies were scarred with craters from impact. Many of the asteroids and comets also carried water and organic molecules, which may have played a crucial role in the development of life on Earth. As time passed, the solar system settled into the stable arrangement we see today. The planets found their orbits, the asteroid belt between Mars and Jupiter remained filled with rocky debris, and the icy objects of the Kuiper Belt and Oort cloud formed a distant boundary around our solar system. But the story of our solar system is not over. Even today, it continues to evolve. The Sun, now in the middle of its life, will eventually run out of fuel in about 5 billion years. When that happens, it will expand into a red giant, swallowing the inner planets before shedding its outer layers and leaving behind a white dwarf. The planets that remain will continue to orbit this dead star, drifting slowly through the galaxy. For now, we live in a time when our solar system is stable, a peaceful oasis in the vastness of space. But it all began with a cloud of dust and gas billions of years ago, shaped by the same cosmic forces that continue to shape the universe today. Life in the universe is one of the greatest mysteries of all time. For centuries, humans have looked up at the night sky and wondered if we are alone, or if other forms of life exist beyond our tiny world. With billions of galaxies, each containing billions of stars and countless planets, the possibility of life elsewhere seems almost certain. But where is it? What would alien life look like? And how could we ever find it? To understand the potential for life in the universe, we must first look at how life emerged on Earth. Billions of years ago, our planet was a harsh and violent place. Volcanoes erupted, meteors rained down, and the atmosphere was filled with toxic gases. Yet somehow, in the midst of all this chaos, life found a way to begin. Scientists believe that the first life forms appeared in Earth's oceans around **3.5 to 4 billion years ago. Simple molecules combined to form more complex structures, eventually leading to self-replicating organisms. These tiny, single-celled organisms would later evolve into all the life forms we see today. But if life could emerge on Earth, then could it not also appear elsewhere? The most basic requirement for life as we know it is liquid water. On Earth, every form of life depends on water in some way. So when searching for extraterrestrial life, scientists often look for planets or moons with signs of liquid water. One of the best places to search for life in our own solar system is Europa, one of Jupiter's largest moons. Beneath its thick, icy crust lies a vast ocean, kept warm by the gravitational forces of Jupiter. This ocean could contain the conditions necessary for life, just like deep-sea hydrothermal vents on Earth, where strange creatures survive without sunlight. Another promising world is Enceladus, a small moon of Saturn that also has an underground ocean. Giant geysers of water vapor shoot out from its surface, suggesting that the ocean below might be interacting with the rocky core, creating an environment that could support microbial life. Mars, our neighboring planet, once had rivers, lakes, and even oceans. Though today it is dry and barren, signs of ancient water still exist. If life ever existed on Mars, it could have left behind microscopic fossils beneath the surface. Future missions, like the Mars Sample Return mission, may one day provide us with the evidence we need. But what about life beyond our solar system? In recent years, astronomers have discovered thousands of exoplanets, planets that orbit stars outside our solar system. Some of these planets exist in the habitable zone, the region around a star where conditions are just right for liquid water to exist. One of the most famous exoplanets is Proxima Centauri b, which orbits the closest star to our Sun. It lies in the habitable zone and could have a climate suitable for life, but we still don't know if it has an atmosphere or liquid water. Then there's the TRAPPIST-1 system, a collection of 7 Earth-sized planets orbiting a small, cool star. 3 of these planets lie in the habitable zone, making them prime candidates for hosting life. Scientists are eagerly studying their atmospheres to look for signs of oxygen, methane, or other gases that might indicate biological activity. But what kind of life might we find? On Earth, life comes in many forms, from tiny bacteria to massive blue whales. But the majority of life on our planet is microbial, existing in places as extreme as boiling hot springs, deep underground caves, and even inside solid rock. This suggests that alien life, if it exists, might not be intelligent or even complex. It could simply be microbes surviving in harsh environments. However, there is also the possibility of intelligent life. With so many planets in the universe, some scientists believe that advanced civilizations may exist somewhere among the stars. The Fermi paradox questions why, if intelligent life is common, we have not yet detected any signs of it. One possible answer is that advanced civilizations are extremely rare or short-lived. Another theory is that alien life exists, but it is either too far away or deliberately avoiding contact. One way scientists search for intelligent life is through radio signals. Projects like the Search for Extraterrestrial Intelligence, SETI**, use massive radio telescopes to scan the skies for signals that might come from advanced civilizations. So far, no clear signals have been found, but the search continues. There is also the possibility that alien life is so different from us that we wouldn't even recognize it. Life on Earth is based on carbon and water, but what if life elsewhere was based on silicon, methane, or even something we cannot imagine? As our technology improves, so do our chances of finding life. Future telescopes, like the James Webb Space Telescope, can analyze the atmospheres of exoplanets in greater detail, looking for chemicals that may be produced by living organisms, and robotic missions to Europa and Enceladus could directly search for signs of life beneath their icy surfaces. But perhaps the biggest discovery would be finding life beyond Earth, even if it is just a single microbe. Such a discovery would prove that life is not unique to our planet, and that the universe may be teeming with living beings. In the vastness of the cosmos, with its countless stars and planets, the chances of life existing elsewhere seem overwhelmingly high. Yet, until we find direct evidence, we are left to wonder, are we alone? Or is the universe filled with life, waiting to be discovered? The idea of humanity becoming an interstellar species, one that can travel between the stars, explore distant worlds, and potentially colonize other planets, has fascinated scientists and science fiction writers for generations. It's a dream that seems to belong to the far future, but is it really possible? Could we ever leave our home planet and spread out across the galaxy? To answer this question, we need to explore the challenges, the technology, and the possibilities of interstellar travel. First, let's consider the distances involved. The nearest star to our Sun, Proxima Centauri, is **4.24 light-years away. A light-year is the distance that light travels in 1 year about **5.88 trillion miles, or about **9.46 trillion kilometers. So, to travel to Proxima Centauri using current technology would take tens of thousands of years. Even the fastest spacecraft humans have ever built, like Voyager 1**, which travels at about *38,000 miles per hour, would take over 70,000 years to reach the star. These distances are so vast that they make the idea of traveling to other stars seem almost impossible with today's technology. But just because it seems impossible doesn't mean it is. Humanity has always pushed the boundaries of what's possible. Consider the incredible advancements we've made in space travel since the first moon landing in **1969 **. Spacecraft that used to take months to travel to the moon now reach the outer solar system in just a few years. New technologies like ion propulsion and nuclear-powered engines could potentially make interstellar travel more feasible. But first, we need to explore the possibilities and challenges of reaching other stars. Let's start with the energy requirements. Traveling to even the nearest stars would require enormous amounts of energy. The current spacecraft rely on chemical propulsion, which is effective for short trips within our solar system. However, the energy required to travel to other stars is far beyond what chemical rockets can provide. We would need a propulsion system that can generate far more energy in a much more efficient way. One promising idea is nuclear fusion, the same process that powers the sun. If we could harness the power of fusion, we could create engines that produce immense amounts of thrust while using much less fuel than traditional rockets. Several theoretical spacecraft designs like the Project Daedalus and Project Longshot have proposed using fusion or even matter-antimatter reactions to propel spacecraft to a significant fraction of the speed of light. With this kind of propulsion, it might be possible to reach the nearest stars in just a few decades or centuries, instead of tens of thousands of years. Another potential method is ion propulsion, which works by ejecting ions at high speeds to create thrust. This technology is much more efficient than chemical rockets, and it's already been used on missions like NASA's Dawn spacecraft, which explored the asteroids Ceres and Vesta. While ion propulsion is not powerful enough to get us to another star quickly, it could still be used for slow, long-term journeys, potentially taking humans or robotic probes to distant parts of our solar system and beyond. There's also the idea of sailing through space. This might sound like science fiction, but it's based on real science. Light sails are thin, reflective sheets that use the pressure of light from stars to push a spacecraft forward. By harnessing powerful lasers or the sun's radiation, light sails could eventually accelerate spacecraft to a significant fraction of the speed of light. This could make journeys to nearby stars much more feasible. Breakthrough Starshot, an initiative launched by scientists, aims to send tiny light sail spacecraft to Alpha Centauri, our closest star system, within a generation. These probes would travel at 15 to 20% of the speed of light, reaching Alpha Centauri in just *20 years. But even with faster propulsion methods, there are still huge challenges ahead. One of the biggest challenges is sustaining human life during interstellar travel. While short missions within our solar system only require a few months or years of life support, a trip to another star could take decades, if not centuries. How would humans survive such a long journey? One possible solution is to create self-sustaining ecosystems. These ecosystems would rely on closed-loop systems that recycle air, water, and food, much like Earth's natural systems. Astronauts on long missions to Mars or the Moon could potentially live in these sealed habitats for extended periods. But on an interstellar voyage, these systems would need to be much larger and more efficient. For centuries, humans have looked up at the night sky, wondering what lies beyond the stars. Our ancestors dreamed of reaching the Moon, and that dream became a reality in 1969 when astronauts set foot on its surface. Since then, space exploration has advanced in leaps and bounds, with numerous space missions, satellites, and rovers exploring distant planets and moons. Today, the International Space Station (ISS) serves as a laboratory where humans live and work in space, performing experiments that benefit life on Earth and pave the way for future missions. But what does the future of humanity in space look like? Where will we go? And how will we get there? Let's begin with the most immediate and achievable goal: establishing a human presence on Mars. For many years, scientists and engineers have been working towards sending humans to the Red Planet. Mars has always been the most likely candidate for human colonization because it shares similarities with Earth, such as the length of its day, the presence of seasons, and signs of past water. However, the challenges of living on Mars are immense. The journey to Mars will take approximately 6 to 9 months, depending on the alignment of Earth and Mars. During this time, astronauts will be exposed to space radiation, which could have harmful effects on their health. This presents one of the first major obstacles for long-term space travel. How do we protect humans from radiation? Solutions might include thick shielding, underground habitats, or advanced spacesuits designed to block radiation. Once astronauts reach Mars, they will need to establish habitats capable of supporting life. This means creating systems to provide air, water, food, and shelter in a harsh environment. Mars has a very thin atmosphere, which offers little protection from radiation and extreme temperatures. It's also extremely cold, with average temperatures around -80 degrees Fahrenheit, -60 degrees Celsius. The first Martian habitats will likely be built using inflatable modules or habitats constructed with local materials, such as regolith, the loose soil and rock found on Mars. These habitats would need to be self-sustaining, recycling resources and utilizing local materials to grow food and generate oxygen. In addition to the challenges of building habitats, transportation on Mars will require advanced technology. The surface of Mars is rocky and uneven, with huge dust storms that can last for days or even weeks. Specialized vehicles will be needed to navigate the terrain and transport astronauts and equipment. One possibility is the development of rover-based habitats, which would allow astronauts to move from one location to another while remaining in a protected environment. There is also the possibility of using drones and robotic systems to explore Mars and assist with construction tasks. As technology progresses, we could see permanent settlements on Mars within the next few decades. Private companies like Elon Musk's SpaceX are working towards making this a reality, with plans to launch missions to Mars in the 2020s and 2030s. SpaceX's Starship is a spacecraft designed to carry large numbers of people to Mars, with the goal of eventually creating a self-sustaining city on the Red Planet. This ambitious vision could be the first step in humanity's expansion into space. But Mars is just the beginning. As we look further into the future, the next major milestone will be the colonization of other planets and moons in our solar system. Venus might seem an unlikely candidate due to its extreme heat and toxic atmosphere, but some scientists propose that humanity could build floating cities in the upper atmosphere. where temperatures are more moderate. Jupiter's moons, such as Europa, are considered some of the most exciting places for future exploration because they may have subsurface oceans beneath their icy crusts. These oceans could harbor life, and if they do, they might become the target for future human missions to search for extraterrestrial life. The potential for life beyond Earth is one of the driving forces behind space exploration. As we expand our reach into the cosmos, humanity may discover signs of life in places we never expected. Extraterrestrial life might exist in the form of microorganisms on Mars, or deep within the icy oceans of Europa or Enceladus. Finding life elsewhere in the universe would have profound implications for humanity, not just for science, but for our place in the cosmos. If life exists beyond Earth, it could change our understanding of biology, evolution, and our own origins.